Cuckoo. Thank you. So the aim of my talk is, as Glenn said, to discuss the asymptotic symmetry group of asymptotically locally empty de Sitter and de Sitter spacetimes, which are relevant both for classical cosmology and quantum gravity perspectives. As you may know, the ADS case has been widely discussed in the literature up to now, but mainly with conservative boundary conditions, so represented here. In this kind of boundary conditions, you don't allow some flux coming from gravitational radiation or null radiation to pass through the conformal infinity of ADS. So in that case, you get, for example, in 4 dimensions, finite asymptotic symmetry group or trivial. And more importantly, these kind of boundary conditions are non-exportable in asymptotically de Sitter spacetimes because, as you see in the Penrose-Carter diagram here, if you impose future boundary conditions here, you will constrain the Cauchy problem reversely back in time. And it's not the usual way to think about the initial value problem in general relativity because actually you impose initial value on a Cauchy slice here and you let your system evolve freely under the equation of motion. So the main point of my talk is that today we have to study leaky boundary conditions in asymptotically locally DS spacetimes because it's mandatory in that case, but also in asymptotically locally ADS spacetimes. For example, you can find recent discussions about black hole evaporation paradox in ADS, and some constrictions need some flux coming out from the spacetime. So you have such type of constrictions where you put an asymptotically flat spacetime at the boundary of ADS to act as a reservoir for your gravitational radiation that come out from the spacetime here. Or you can study, for example, the systems where you have a brain-world dynamics in higher dimensions bulk spacetimes, where you can explore some holographic dualities with non-trivial quantum gravity induced on the boundary. And with all these motivations, the Lambda-BMS project was born. And the main goal of this project was to uncover the generalization of BMS to non-flat asymptotics together with a quest for leaky boundary conditions in that context. And in fact, the two quests are equivalent because you can observe that you cannot get an infinite dimensional asymptotic symmetry group like the BMS group, for example, in the asymptotically locally ADS spacetime without allowing a fluctuating boundary structure. We can reformulate this lambda BMS reflection in one sentence that amounts to find some intermediate boundary conditions which are merely a boundary gauge fixing, which means that these boundary conditions must be always reachable in any gauge by diffeomorphism, and as a result, that will not impose any constraint on the Cauchy problem in the de Sitter case, which is one constraint we want. We can expect from this project some advances in various ways because in asymptotically locally ADS spacetime, we can import techniques and results from the well-known asymptotically flat case. And we can, through a fancy flat limit process, get better understanding of remaining problems concerning the asymptotically flat case after getting the results in the non-asymptotically flat case, as I will explain. The framework I will set here is the standard one. So I will choose the Starobinski-Fefferman-Graham coordinates, whose the coordinate rho is the holographic coordinate represented in this diagram. And I will consider both signs of the cosmological constant. So I set my parameter eta here. And I just I just will impose a minimal follow for allowing for conformal compactification on the dynamical components of the metric, which allow me to give sense to the conformal infinity, which I will denote by scry. I recall that the solution space in Einstein gravity for this setup is the Einstein equation are solved for game AB in a polyhomogeneous expansion in rho, which is completely parameterized by a couple of free data, the boundary metric, and the orographic stress tensor, whose stress and divergence are fixed by the Einstein's equation. The residual gauge diffeomorphism that preserve the Starobinsky-Pfefferman-Graham coordinate system are built up from two sets of parameters. One part is the Weil rescaling in the radial or the orographic coordinate component psi rho. And here, the leading order of the transverse vector is any diffeomorphism on the infinity. In my analysis, I will allow generically for field-dependent parameters, so I will not impose that delta psi1 of psi2 is 0. And I will show that it's very important to keep this freedom here. And so I must use a modified Lie bracket to define my diffeomorphism algebra, which is given by that. Under gauge transformation, my couple of free data will modify as follows. So the boundary metric is modified simply as follows, and the stress, the orographic stress energy tensor will transform homogeneously under diffeomorphism only if D is odd. Because when D is even, you know that if you shift from conformal factor, you are not guaranteed to remain in the same boundary theory, in fact. I just have to mention to end this review part that the symmetries are realized on the solution space as follows. And the solution space, in fact, represents the symmetry group, which reduces to all the diffeomorphism in some ideal product with the Weil rescalings when the gauge parameters are field independent. So now let us take a look on the renormalized variational principle. So apart from the Einstein-Hilbert piece, which is mandatory, and the Gibbon-Soking piece, which ensures the variational principle when the boundary structure is fixed, we know from a long time now that we will need a counter-term Lagrangian built up of covariant structure of gamma, and which is needed when the boundary structure is varied, in fact. And in addition to that, which is the standard orographic renormalization procedure, I will allow for a finite term here in the Lagrangian that I can freely add, which will be diffeomorphism and Weil invariant, and may depend on various background structure that I will explain a bit later. So for all the Lagrangian I've just defined, I can define the associated presymplectic potential as the total derivative term in the variation of the Lagrangian. The author is the equation of motion, as you know. And the symplectic structure of my theory, so the Einstein-Hilbert symplectic structure, is simply the anti-symmetrized variation of the Einstein-Hilbert presymplectic potential. But the latter is divergent when I approach infinity. So in order to define properly my charges, I have to bring the holographic renormalization at the level of the symplectic structure. And to do that, I use the simple ambiguities of the formalism, which are adding a boundary term to the Lagrangian, which changes my presymplectic potential by an exact term. Or since this presymplectic potential is defined here as a total derivative, I can always add the so-called Heuer-Wald ambiguity, which is the total derivative of a codimension 2 form here. And if I choose smartly A and Y to renormalize my Einstein-Hilbert presymplectic potential, I can get a renormalized presymplectic potential, which is finite in rho and proportional in the variation of the boundary structure. And the good prescription to do that is the box formula here. You can compute from this formula the normalized action principle, which is the following. And you see that you will have non-zero symplectic flux to infinity when the boundary structure fluctuates. And for the moment, I will forget about T0 here. So the contributions of my fancy finite Lagrangian. So when you contract the presymplectic current with a gauge variation, you have all you need to define the surface charges as the boundary term in this presymplectic current. You do the computation, so without assuming further than the minimal fall-off allowing for conformal compactification, and you get these charges, which are made always from two pieces. You have the universal part here, which includes the usual Comar term and the higher wall contribution, which is simply the contraction between the symplectic flux at infinity and a gauge parameter psi bar. And when D is even only, you have an additional part which comes from the Weil contribution of the diffeomorphism. And we have a very nice interpretation for that, because you see that for D odd, the Weil transformations are trivial diffeo. So they are not part of the asymptotic symmetry group. Because when you define your asymptotic symmetry group, you have to caution by the symmetries that are associated with vanishing charges. But for the even, these Weil charges are not zero. And it's simply related to the fact that if you choose different conformal factors in the conformal compactification process, that will lead you to physically inequivalent situations, which is the trace of some Weil anomalies at quantum level. Some properties of these charges, they are associated with the most general asymptotically locally DS and ADS solution in any dimension in the Starobinsky-Feverman-Graham gauge, which means that if you give me a solution written in the Starobinsky-Feverman-Graham gauge, I can compute for you the charge associated with the Weil part or the diffeo part. This computation generalizes all previous results in the literature because it arose from field-dependent parameters, gauge parameters. It includes the Weil charges, and it's valid for both signs of the cosmological constant. More crucially, these charges are obviously not conserved because the symplectic flux is not zero through infinity in general. And so the flux balance law here that you may know indicates that the temporal variation of the charge is not zero. This temporal variation gets a various contribution mainly from radiative gravitational degrees of freedom, but also from Weil anomalies. For example, you can have flux in 3D gravity, even though you don't have gravitational degrees of freedom. You don't have gravitational waves. Even more important, these charges are non-integrable, since you cannot directly write them as the total variation of something. And this is not quite surprising, because in presence of symplectic flux at infinity, you are facing with some kind of non-equilibrium physics in which GAB 0, so the boundary metric, will act as a source. And so the results of the integration on the phase space, which give you the final charge from the infinitesimal one, is not expected to be path independent. For this kind of charges, which are not integrable, I have to recall that there is no representation theorem. And so I will use the algorithm proposed about 10 years ago by Glenn and Cédric, and which amounts, first of all, to split the infinitesimal charge between an integrable part and a non-integrable part. This split obviously is ambiguous because I can always subtract and add a delta exact term without modifying my charges. So I will need a physical prescription to fix this split, but I will not discuss that in more details here. In fact, here we were not very inspired, and we just put in the integrable part the Komar part, which is the usual one, involving simply the gauge parameter and the stress energy tensor on the boundary. And the non-integrability is due in this prescription to the higher Wald term, so the symplectic flux, the Weil part, and the field dependence, the possible field dependence of the gauge parameter. But with this split, we were able to check explicitly that the charge algebra closed under the Barnish-Troussard bracket, which is another success for this marvelous result. And the algebra so closes under the bracket defined as follows, but up to a field-dependent 2 cocycle, which I denote here by K, which is anti-symmetric in Xi1, Xi2, and satisfies this cocycle condition in order to ensure that the bracket satisfies the Jacobi identity. The cocycle is in fact 0 for the odd, which could motivate our choice of split, because if you change of split, you can generate some trivial 2 cocycle, what we don't know. For example, in 4 space-time dimension, here you have an algebra which is not centrally extended. But for the even, this K is not trivial in general. I put here the expression for D equal 2 and D equal 4. So you can see that there is some pattern. If this expression, you have the anti-symmetrization here of the sigmas, which we call the form of the 2 cocycle for the BMS group in the flat case when you turn on super rotations. But more importantly, here you have the temporal component of the diffeomorphism always multiplied by the Weil anomaly, in fact. Here you just have the boundary Einstein-Hilbert Lagrangian, and here you have this fancy combination that you may recognize if you are familiar with asymptotically locally ADS gravity. So let me particularize a bit this framework to something that you guys all know very well, which are conservative boundary conditions. And I will take the particular example of Dirichlet boundary conditions, for which I will freeze completely the boundary metric and also freeze completely the symplectic flux to infinity. This leads to a well-defined Cauchy problem in the case of asymptotically locally ADS spacetime, but are discarded for the De Sitter case, as I said in my first slide. So for these boundary conditions, the universal structure you have to preserve is a boundary foliation, which is the time evolution along the ADS boundary cylinder, and a fixed metric on the transverse codimension 2 space. The residual diffeo are the conformal algebra in D dimensions. Since you have fixed the boundary structure and killed the symplectic flux, you are back with integrable and conserved charges, and the charge algebra closes under the standard Dirac bracket. The 2 cocycle is always present, but reduces to a central extension, which is the famous and celebrated Brown-Hainaut central extension for D equal 2, which proves, and I say prove, that the 2 cocycle is non-trivial in general and thus cannot be absorbed by a fancy redefinition of the Hamiltonian. I just have to mention that the cocycle is trivial for D greater than 2 after you have subtracted the ADS vacuum charges. Now let me enter into the fancy part of the game, because if I relax a bit this universal structure by not fixing the transverse metric here, but only its volume form, I can write the boundary metric as follows. And that it's simply a boundary gauge fixing that I mentioned earlier, because it's always switchable by using my diffeomorphism freedom on the boundary and my while freedom on the boundary. So this boundary gauge fixing will not constrain the Cauchy problem in the de Sitter case, which is a very good property. And it's valid for both signs of lambda if you are not against open system in ADS. The of this boundary structure have to satisfy this differential equation, which look like the BMS constraint, in fact, but with something very important, is that this piece is field dependent. It depends on the fluctuating boundary metric. So you get here field dependent gauge parameters. The algebra of the diffeomorphism that solves this equation gets, for that reason, field dependent structure constant, as you can see here, and this term comes precisely from this constraint. So rather than an asymptotic algebra, you get an asymptotic algebroid that we call the Λ-BMS algebroid. And for each point in your phase space, in fact, this Λ-BMS algebroid forms an infinite dimensional algebra. If you are not convinced, you can simply check that if you set xit to 0 and the angular part, which is simply a time-independent divergence-free vector, you get all the area-preserving diffeomorphism on the d-1 sphere, and this is a strict subgroup of Λ-BMS. In 3D gravity, Λ-BMS does not bring more in the game because fixing the determinant of the metric on the cycle completely frees the metric, so you are back to Dirichlet boundary conditions. But from d equal true 4 and so on, you have new things that appear. And in fact, for d equal 3, we find explicit solutions for the background metric to be the unit transfer metric using this Helmholtz decomposition. You can show, in fact, that solving the differential constraint I showed in the previous slide leads to this fancy combination of spherical harmonics. I can just mention now some relation between the symmetry group you all know and this novel Λ-BMS symmetries. If you freeze the source in the asymptotically locally ADS phase space, you are back to the exact symmetries of the vacuum ADS or DS, depending on the sign of the cosmological constant, which are these groups. And if you take the flat limit of these groups, you are back to, obviously, the Poincaré group. But you can take another route. You can take directly the flat limit in this constraint here, which will allow you to get rid of this term. You are back to the BMS constraint, sorry, and you allow the boundary metric to fluctuate. So you don't have just BMS, you have the generalized BMS group with all the tower of diffeomorphism on the two sphere, on the celestial two sphere. Okay. And so when you freeze the sources, in that case, you are back, as you may know, to Poincaré. So this diagram is perfectly commutative. I just have to mention before finishing that the Λ-BMS boundary conditions are in fact leaky for the strictly superior than 2. And that allows from an arbitrary symplectic flux through infinity, which is described by this symplectic form. Okay, you can say to me that that leads to non-globally hyperbolic solution in the case of negative cosmological constant, but in fact you can see it as the dual CFT, which is in coupling with an external system, a reservoir if you want, or a thermal system. But what is important in the formula highlighted in yellow is that the symplectic couples here GAB, so the transverse part of the fluctuating metric, and the trace-free part of the boundary stress energy tensor generalize, in fact, the notion of bonding use in asymptotically flat spacetime. As a corollary of what I said about the generic charge algebra, the Lambda-BMS charges form an algebra that close under the Barnish-Troussard bracket and that are extended by field-dependent 2 cycle for the even, and which is presumably non-trivial at all. But more importantly, this algebra, this Lambda-BMS algebra, contains very precious information about the flux balance law to be uncovered at infinity. In fact, you just have to contract this algebra with the boundary structure, the boundary foliation vector, so with T, which is the time evolution vector in ADS, to fix the IDS, and the second diffeomorphism, which is an arbitrary Lambda-BMS gauge parameter, and you get this formula, which is the analog of the Walsh-Zupas flux formula for asymptotically flat spacetimes, and it's a particular case of the general Strominger and Enos-Seng formula in the context of asymptotically de Sitter spacetime, but considering all the diffeomorphisms. And so, since, as usual, I am running out of my time, I will skip directly to the conclusion without making further comment on the flat limit. So, the main punchline of my talk were that leaky boundary conditions in asymptotically locally ADS spacetimes are appealing and is a very interesting route of research today. I presented for you the most general renormalized phase space in D+1 dimension with very minimalist boundary conditions. During the route of this project, we got another evidence for the Barnish-Troussard algorithm and for the Barnish-Troussard bracket. And we demonstrate that using a fancy boundary gauge fixing, you can find an infinite dimensional Lambda-BMS algebroid as the most natural extension of BMS to non-asymptotic flat cases. I just mentioned here that we have also a good control on the flat limit in 4 dimensions at the level of the phase space or at the level of the charge algebra, but we have to perform 2 fancy things. You have to change of coordinates. You have to go in Bondi gauge, in fact, because in that gauge, the flat limit is well defined and the Bondi gauge exists for any type of asymptotics, whereas lambda is 0 or not, it's not a problem in that case. But at the level of the phase space, to renormalize the symplectic structure, which is divergent when you take lambda to 0, you have to include some kinetic corner terms for the fluctuating boundary metric in the variational principle. So the future directions for this Lambda-BMS project is to study this Bondi phase space in any dimensions and its flat limit, because we need Bondi Sachs coordinates to perform the flat limit. And we would like to relate the result in ADS holography with the new result in flat holography, all this fancy stuff with celestial sphere CFT and so on. But there are many open questions raised by this project. What's the link, for example, between the Lambda-BMS symmetries and the memory effect in cosmological cases? What's the exact content of the Lambda-BMS phase space? Are there new ADS or DS black holes? What is the role of the Robinson-Trautmann solution and stuff like that? And finally, a personal dream is to get, after so much evidences for the Barnish-Troussard algorithm, finally a general proof for the Barnish-Troussard algebra and a general discussion about the 2 cocycle which come within this algebra. So I said mostly everything I wanted to say, so thank you for your kind attention.
Thank you, Adrien. Any quick questions to Adrien, because otherwise we're going to accumulate too much delay. So
sorry to be long.
I see a question in the chat. Maybe you can ask it directly. So from Fabio. So, well, maybe this is a better question for the chat, I would say. So any other questions to Adrien?
I have one.
Please.
So I go?
Sure.
Well, my question is, do you see any sign of this structure on the CFT side? So if you think in terms of ADS CFT, would you expect on the CFT side to have more symmetry, enhanced symmetry structure?
We didn't explore this this part of the project yet, but a comment that I can make about this question is that it's not the usual ADS CFT correspondence you can think about, because here we will face with some deformed CFT due to the coupling with an external thermic bath or something like that, because you are facing with open systems. But if ADS CFT always holds in that context, I will expect that the Λ-BMS symmetries will be the exact symmetries of the dual theory as well.
Okay.
But I did not have any proof of that.
So, Charles, maybe if you have a question.
Hi, Adrien. I had a question about this Troessaert algorithm. So there is an ambiguity in choosing what you call non-integrable and what you call integrable part.
Yes.
And the central charge, I think, if I remember well, is dependent on this ambiguity.
In fact, if you shift the integrable part by some quantity and you cancel it by subtracting in the non-integrable part, you will shift the two co-cycle by a trivial co-cycle.
Okay. Okay, good.
But
that's
here,
very
here the point is that you cannot completely get rid of this co-cycle because it contains the Brown-Eno central charge at some limit for some boundary conditions.
Okay. Okay.
Okay.
Okay. Thank you. And maybe a follow-up question. Should I understand? Should I imagine that the fact that there is a leak? Should I imagine that means that I should consider a bigger theory where I couple gravity to something else, and that in this theory, if I were to compute the charges, I would get something integrable, or is there something deeper than that? I'm just trying to understand what should we do with non-integrable charges, and what is this bracket basically?
Up to, and I say up to my understanding, the non-integrability is mainly due here to the flux at infinity, as you mentioned. And so I expect that, yes, if you include say the reservoir or the thermal bath into the game, yes, you have the whole system, and in that case, you will be able to deal with integrable charges.
Okay.
But
Okay.
if somebody can correct me if I am wrong, please do it. But
maybe we should keep the rest of this discussion for the coffee break. It's interesting, of course, but maybe let's have another couple of quick questions. So also Laura had a question.
Yes, I had a question.
Sorry.
I thought there was, sorry, Laurent, go ahead.
Oh, sorry, you can go, Sean. So,
No, go ahead.
Okay. Thank you, Adrien, for this beautiful talk and this beautiful result. I want to comment back on this ADS thing. So, I mean, what you're doing is very important, but you also, I want to emphasize that, and I want to see if you agree. What it implies, it's a profound challenge on the usual ADS CFT story. So let's say ADS CFT story, as the two tenets of ADS CFT story are, first, that it's unitary, that is, there's no symplectic flux, and two, that the boundary theory is non-gravitational, that is, the metric does not fluctuate. And from people in quantum gravity, we know for a long time that has been always in conflict with what we find. When we quantize gravity, there is no way we can keep the boundary metric classical unless you really restrict inside the phase space. So I want to see whether you agree that in some sense it's a complete reset on ADS-CFT picture, which is very nice.
Yes, and in fact, as I said to Marc, it's a route that I have not explored yet, but yes, we will expect to have some deformation of the boundary metric, but it's kind of profound, as you mentioned, but I'm not a specialist of ADS-CFT. The only thing I can say is that we will have to change the mind in order to include this fluctuating boundary metric into the game in ADS-CFT. And I guess that it will be possible if you include in this fashion some reservoir at the exterior of space-time. I guess you can recover the unitarity in the whole setup when you include this this external system coupled with your space-time.
Okay. Thank you, Andrea. Laura, maybe you one quick. Okay, let's really resume this in the coffee break. I'm sorry, but Marc is going to speak and he's already lost 5 minutes. So meaning, no, Laura, you one quick question. Also.
Yeah, quickly. No, I was wondering whether you could see the structure at I0, or how could you do this from your analysis? At
I0, you mean in flat space or in ADS?
Yeah.
In flat space?
Yeah.
We did some kind of analysis at I0, but it will be a bit long to explain now. But just to summarize, when we take the flat limit, we get the generalized BMS charges, in fact. And we showed that we can select an Hamiltonian, which is 0 for vacuum configuration, including the superrotation sector of the theory. And with this Hamiltonian as an integrable part, we showed that, in fact, the standard Dirac bracket closed without any central extension at spatial infinity and at future time infinity. So that restores the full generalized BMS group in some sense at spatial infinity, including all diffuse-2 superrotations. But it's not a constructive argument. It's an argument from the algebra of the charges.
Okay, thanks.
I can present you more details a bit later.
Andrea, one question from you as well. Andrea, do you have a question?
Yes, sorry, I could not mute myself. I think it's not a short question because I wanted to hear a bit more about the flat limit and these corner contributions. But,
let's keep it. Is it okay for you to keep it for the coffee break together with Laurent? And,
sure.
Okay. Alfredo, do you have one question for us?
Yes, a very small question. Here you use the Eyer-Wald method, which we know that contain an ambiguity that you use basically to remove the divergences. But what occurs if you use the Babnitz-Brand method to compute the charges? Are they finite?
I don't have any idea how to renormalize the charge in that context. Because the charges are simply defined from the equation of motion, so they are fixed. I have no key to push to renormalize if you want the charge. So I have no idea about it.
Okay, very good. So I suggest that you unshare your screen and so that we can get Marc going. And
okay, so
Marc has 10 more minutes and coffee break is only going to be 5 minutes now. So please, Marc, is it working for you? Can you share?
Yes. Should work now. Do you see my screen?
Very nice. Yes, please go ahead.
Okay, let me just go full screen.
I will not introduce you, right? I just let you talk.
Okay. Can you hear me also?
Perfect.
Okay, thanks. So yes, first of all, thanks to the organizers for the kind invitation, and thank you all for tuning in. Yeah, I'm happy to give this talk because I think I may be a bit of an outsider. So I'm happy to be able to give the perspective of an outsider.
And in particular, I apologize because I'm going to go maybe against the topic of the workshop, because I'm going to talk about prospects at a finite distance. So the motivation for this work, and I think the motivation for all of us probably, is to learn something about quantum gravity. And it's probably clear from our understanding of classical physics and also quantum physics that a central role in the quest for quantum gravity must be played by symmetries. But what is not clear is what type of symmetries. So which symmetries are we talking about exactly? And a related question, of course, is the question of what are the fundamental degrees of freedom of quantum gravity, and where do these degrees of freedom live? What are these degrees of freedom assigned to? Now, a slightly finer question is, what does quantum gravity assign to lower dimensional objects? So for example, boundaries, or we could even think of the question of what quantum gravity assigns to points. And we know, for example, from even simpler theories like topological quantum field theories, that if you want to extend them down to the point, we see very intricate and complicated structures that are assigned to lower dimensional submanifolds. Then a related question is the question of how to make sense and how to define subsystems, because any realistic experiment is done, let's say, in a bounded region of space-time. And if we define subsystems, this is typically something very complicated to do in a gravitational theory or in a gauge theory. And if we can have a definition of subsystems, how do we make sense of kind of the gluing and putting subsystems back together? But nicely, we have had many pieces of answers from very different approaches. So the prospect is to try to kind of merge these different pieces of answers together. And in particular, just to take two more specific examples, which are interesting for us today, we have all the insights and all the tools and the contributions from ADS-CFT and more general approaches to holography. And in a sense, we could say that the focus has been more on the boundary, and the challenge in these approaches has been to reconstruct the bulk geometry of space-time. And there's a bunch of other approaches, which I here refer to as loop quantum gravity or covariant versions of it, spinfold models, and also all relative approaches to quantum gravity, which have so far focused more on the bulk and kind of neglected physics and phenomena happening at the boundary. But the idea is that we should maybe try to merge these two things together, because there are already many insights and many tools available, and we can try to think of the picture which would arise. So I'm going to try to argue today that if you try to merge these things together and get a consistent picture, we kind of get places where things start to match, and this is, I think, encouraging. So the picture is these little, as represented here, these little bubbles glued together. And this is a proposal for what we could call quantum gravity at the corner. So this is a proposal which is based on a notion of local holography. And the idea here is to focus on the symmetry content for arbitrary subregions at finite distance and boundaries of these subregions, which from now on I'm going to refer to as corners. So corners are codimension to boundaries. And the idea is that once we understand, as we expect from quantum theory, if we understand the symmetry content of the theory, we can go towards the quantization and understand the building blocks by quantizing these symmetry algebras. So we want to associate Hilbert space and states and quantum numbers to these corners. And we want to think of the degrees of freedom of quantum gravity as being organized by the representation of these corner symmetry algebras. Then once we understand the representation and the organization of these corner degrees of freedom, we want to be able to ask the question of how to reconstruct the notion of space as an entangling and a fusion of these corner degrees of freedom, and then try to think of the dynamics in terms of the evolution of the charges and these quantum degrees of freedom. If we phrase this in a slightly different context, maybe this will start to make a bit sound more reasonable. What we have learned in recent years is that there is extremely rich structure encoded in what is now known as the infrared or Strominger triangle. And this infrared triangle is a relationship between three key things, which are the tip of the triangles. So something which has to do with quantum field theory. So sorry, the soft theorems. Then on top, we have the memory effects, and we have also a notion of asymptotic symmetries. But it's kind of reasonable, I think, to ask if it's possible to bring this triangle from the infrared to make sense of some notion of a finite distance Strominger triangle. And in this finite distance triangle, we could ask the question of what is the equivalent of non-perturbative memories. And on the bottom right-hand side, we could replace the notion of asymptotic symmetries by finite distance symmetries, so-called corner symmetries. And of course, the bottom left point of the triangle is what we are looking for, because we don't know how to kind of embed all these results about, for example, the Weinberg soft theorems into completely, make them into completely non-perturbative statements about quantum gravity, because we don't know what quantum gravity is. So this is why I added these two little arrows here on the sides of the triangle, because the hope could be to try to use the notion of corner symmetries and a description of these non-perturbative memory effects in order to try to define a theory of quantum gravity. So the question is whether we can define the other two tips of the triangle and then somehow use this to define a notion and a theory of quantum gravity. So to do this, the starting point, so a good place to start is to try to understand what happens with these corner symmetries. So the setup for this and the tools. So the starting point is the familiar observation that when we have boundaries in a gauge theory, and in particular gravity, the boundaries have the ability to turn gauge symmetries into physical symmetries. This means that you have a non-trivial charges and algebra of charges at codimension 2 corners S. Now, as you also know, this is best studied in the so-called covariant phase space formalism, which was developed by many people, some of them present in the audience. And that can be also formulated with kind of slightly different mathematical perspectives. But for us here, the idea will just be the familiar thing that you have a Lagrangian, and upon computing its variation, you get the equations of motion and a boundary term, which gives you the symplectic potential. What we want to get is a classifying criterion for different formulations of gravity, and this will turn out to be the corner symmetry algebra. To do so, what I want to propose is to kind of increase the complexity step by step and start at the 0th simplest level. This is to consider kind of fixed corners called entangling spheres without boundary conditions, no time evolution, and tangent diffeomorphisms. Then to go on, we can realize first a very simple result, which will help us understand this idea of having different corner symmetry algebras to classify different formulations of gravity. So the simple result is that for any formulation, which we call F, of the same theory, namely theory of gravity, the symplectic potential can always be written as a sum of two contributions. One contribution is a universal bulk piece, which you can think of as being the piece of canonical ADM GR. So I will call it GR for the rest of the talk. And this gives a component of the corner symmetry algebra, which is just a diff of the corner, diff S. Then on top of this bulk piece, there is a corner piece. And I want to argue that this corner piece brings extra charges and contributions to the corner symmetry algebra. So if we take this seriously, it tells us that different formulations of the same theory can have different corner algebras. And then if we take seriously the point that quantizing and building representation theory of these corner algebras can lead to potentially inequivalent quantizations. And this is a theme which has been present in the field of quantum gravity since now almost 20 years, that we can kind of achieve and construct different formulations of quantum gravity based on different classical starting points. So this is kind of the symmetry and the covariant phase space version of this statement. So if I make this statement, now we have to illustrate it and see more precisely how this works. So to illustrate this, the simplest place to do this is, of course, in familiar 4D metric gravity. And so the starting point is the usual Einstein-Hilbert Lagrangian. So epsilon here is just the volume element. And so this is the Einstein-Hilbert Lagrangian, epsilon r. Now I write this very familiar expression for the symplectic potential, which is the first line. That's just what you get from the variation of this Lagrangian. And then a little bit of rewriting shows you that you can write this Einstein-Hilbert symplectic potential as a sum of 3 terms. One of these terms here is just a total variation. So this we can forget about, but what is more important is that there is, as claimed, there is a bulk piece, which is theta gr, so the canonical general relativity potential, and there is a total derivative, which is the corner piece, which features the 2 normals to the codimension 2 corner. Now this result is not, shouldn't come as a surprise to you, because one reason for this, behind this simple result, is that this is due to the familiar fact that we can actually relate the Einstein-Hilbert Lagrangian to the so-called ADM or Hawking-Hunter Lagrangian. And the relation is just with the familiar boundary term, which depends on the acceleration and the extrinsic curvature. But in fact, there is a deeper reason behind this. And the deeper reason, I think, is that it really follows from the fact that if you actually focus on this relative Lagrangian, so the relative Lagrangian is the Lagrangian which takes you between these 2 different formulations of the same theory, so which takes you from the GR Lagrangian to the Einstein-Hilbert Lagrangian. If you actually take the variation of this Lagrangian, you can show that you, just out of it, by this variational formula, you get the Einstein-Hilbert and the GR potential, and you get this corner term d theta. So this is telling us that boundary Lagrangians, they generically have their own symplectic potentials. And these symplectic potentials of boundary Lagrangians, we should take them into account, and they contribute naturally as corner terms. So this is a viewpoint that has been developed recently by some of us, and also by the covariant phase space with boundaries of Harlow and Wu. And I think this is kind of consistent with the fact that we want to, define a theory and assign physics and data to all possible lower dimensional submanifolds. So in particular, the boundary has its own Lagrangian, and this Lagrangian carries its own symplectic potential. So taking this point of view tells us that these corner terms, they are not ambiguities. Rather, they are features of the theory. And because of these features, that's the reason for which different formulations of the same theory can have different charges and different algebras. Now we can continue illustrating this in the case of gravity, and we can ask what happens to the charges and the generators. So again, the very familiar result is that if you consider a diffeomorphism acting by Lie derivative, once we contract this with the symplectic structure, we get the bulk piece, which is just the spatial diffeomorphism constraint, so the conservation of the ADM momentum. And of course, this bulk piece agrees in both formulations. For the GR bulk charge and the Einstein-Hilbert one, they are the same spatial diffeomorphism constraint. And then, of course, the algebra of this diffeomorphism constraint is just this Lie algebra of with the bracket of vector fields. But now a more subtle question and a more refined point is to ask exactly how this algebra is represented in both formulations. And if we ask exactly how this bracket is represented, so we do this by looking at the corner charges and the algebra, then we realize that because the 2 theories have a symplectic potential that differ by a corner term, they don't have the same charges. So in the GR formulation, we get the familiar Brown-York charge. And we can notice, for example, that this charge has the property that it vanishes if the vector field is vanishing at S. And this charge contributes to the corner algebra only with the component which is diff of the corner, diff of S. But on the other hand, the Komar charge, which we obtain in the Einstein-Hilbert formulation, has a different property because it features a derivative of the vector field. So because of this, it can be non-vanishing, even if the vector field is vanishing at S. And because of this, if we zoom a bit on the structure of the Komar charge around the codimension 2 surface, so this can be nicely done by using a 2+2 decomposition, then we notice that there is an extra contribution to the algebra, which is an SL2R algebra, so an ultra-local SL2R algebra, so at each point of the surface. So this reveals indeed that this notion of corner symmetry algebra is different and is slightly larger in the Einstein-Hilbert formulation than it is in the canonical GR formulation. And this is due to the presence of this corner contribution to the potential and to the symplectic structure. So if you just put this simple observation in a table, and also to spoil a bit what is coming in the rest of the talk, we can put here the different formulations of four-dimensional gravity, and on top we can put the different corner symmetry algebras which we get. And we have already an example where this differs, and we want to understand what is the underlying structure behind this. So if we go back to our motivations now, this is kind of illustrating on a simple example that different formulations of the same theory, gravity, reveal different components of the corner symmetry algebra. So if indeed it turns out to be true that this corner symmetry algebra plays a role in the quantization of gravity, it is legitimate and it is necessary to ask the question of what is the full symmetry algebra. If we have a full and a notion, if this can be defined, of bigger symmetry algebra, this means that upon quantization, we have more quantum numbers or more handles to reconstruct what happens inside of the region. So the bulk degrees of freedom and the dynamics of these degrees of freedom. So my goal for the rest of the talk is to continue now justifying and arguing why this indeed has to do and contains some aspects of quantum gravity. I also want to explain that looking at extra components of this corner symmetry algebra has indeed physical content and physical implications, and that looking at different formulations of the same theory can also reveal aspects of dualities and things which are not maybe obvious to see if we don't look at the right formulation. And this is something which, a theme which has also appeared in this study of asymptotic symmetries and the infrared triangle, because we know, for example, from the work of, it was motivated again by the work of Strominger, that there is probably a notion of magnetic charges in electromagnetism. There is also a notion of dual charges in gravitational theory, and even for a scalar field, there is a notion of soft charges, but these soft charges, they only take a gauge interpretation once we dualize the scalar field. What we can ask is, what is kind of the, if there is a principle which can tell us how to reveal the maximal amount of charges that a given theory should have. So to kind of continue illustrating this, I want to first start with an example in 3 dimensions, and then keep going to 4 dimensions. So the example in 3 dimensions is to consider the most general first order Lagrangian. So this is something known as the Milky-Beckler Lagrangian. And this Lagrangian is just a simple sum of 4 terms, all of which you should recognize. So the first term with coupling sigma 0 is just the volume term, so a cosmological term. The second term with coupling sigma 1 is just the familiar Hilbert-Palatini term. Then you have a Chern-Simons term for the spin connection omega. And then you have a torsion term with coupling sigma 3. So this is a first order formulation where omega and E are the independent fields. And this Lagrangian is that of a topological theory. So there are no degrees of freedom. And to see what this describes, you can compute the 2 first order equations of motion. And upon a bit of rewriting, you find something which is kind of looking nicely symmetrical. You find that this is a theory with a source of Lorentzian curvature measured by the parameter P, which is a function of the coupling sigma, and a source of Lorentzian torsion measured by the parameter Q. Now, as usual, you can combine these 2 first order equations of motion and combine them to get a second order equation of motion. And this is just the familiar Einstein equation with an effective cosmological constant, which is a function of P and Q. So there is already something peculiar here. You notice that in the first order formulation, you have these 2 parameters P and Q, but there's infinitely many choices of P and Q, which can give you a value of capital lambda. So this means that the same metric geometry can be defined by infinitely many different parameters in the first order formulation. So this will kind of naturally find an echo once we start to understand the charges of this theory, because this begs the question of how the first order charges are related to the metric charges. So again, this idea that looking at different formulations of the same theory can reveal different aspects of the corner symmetry algebra. So to go on, we have to look at the potential of this theory. So doing it, in our heads, like Daniel explained this morning, we can just look at where the derivatives sit in the Lagrangian and see that the potential is again a very symmetric expression. It has delta omega and delta E and all three possible terms. So this is why this is the most general thing you can write down in 3 dimensions. Now, to understand the charges, we have to look at the symmetries of the theory. So the symmetries are given by the familiar internal Lorentz transformations. So rotating E and acting on the connection as covariant derivative. And on top of these, you have what is sometimes called the translations. So the translations, they act on E and omega in this form, which is written here. You can easily check that these are symmetries of the Lagrangian. And now on top of these internal gauge transformations, you have, of course, diffeomorphisms. And because this is 3D gravity, because it's a topological theory, diffeomorphisms have the property that on shell of the equations of motion, which are written here, diffeomorphisms can be written as field-dependent internal gauge transformations. So this is the statement, it's the last equality, which is written here. Now we have to go to the covariant phase space formalism and look at the charges corresponding to these symmetries, namely Lorentz transformations, translations, and then ask the question of diffeomorphisms.
Just may I ask a question here?
Yes, yes.
It was just by your choice that you called E the tetrads or the triads and W the spin connection.
Yes.
You could have taken any linear combination of them because these are just non-forms, right?
Yes, that's true. Yes.
So I would expect that there should be some extra symmetry coming from the choice of metric, what you call metric.
By metric, you mean
so basically, you can take any linear combination of E and W and square that, and you declare that that's the metric.
Yes, that's true. Yes.
This is just okay. So I expect that this should be a part of the symmetries that you will eventually show us.
Yes, I think you could also realize these symmetries. Yes.
Okay, thanks.
Yeah, maybe it will echo to what I will show you in a moment. Yes.
And Mark, just to make sure, this is just the sum of two Chern-Simons, SL2 Chern-Simons with you, right? With unequal level.
Yes, with a little subtlety that I didn't want to get into, but so indeed one could ask what is the Chern-Simons formulation of this theory, and there is a little subtlety because you see that the theory here has 4 different couplings, and if you use the if you write this as a Chern-Simons theory, you get 3 independent.
But I can read the whole Lagrangian, and also I can also absorb in E perhaps. So in the end, I may leave. I mean.
Yes, but yeah, so you can write this. In fact, yeah, you can write this as it is most elegantly written as a Chern-Simons theory for these symmetries which are written here, the Lorentz transformations and these translations. But I can go back to this later if you
maybe indeed later because
yeah.
We're running late. You have 5 more minutes, Mark. Sorry about that.
Yeah. Only 5 more minutes. Okay.
Well, a bit well, 5. Yeah.
Okay. So maybe I'll try to. It's not very complicated. So it's just to illustrate the fact that you look at the charge algebra of this theory, and of course you get the current algebra formed by these Lorentz transformations and translations. But now the nice thing is that if you look at diffeomorphisms, you see appearing naturally a notion of dual diffeomorphisms. So as I said, diffeomorphisms are field-dependent gauge transformations. And if you look at diffeomorphisms here, these usual diffeomorphisms are always defined, but then there are 2 sectors of the theory, namely when either curvature is vanishing or torsion is vanishing, where you can define these 2 other generators, which are integrable and well-defined on phase space, B and C. And just to summarize here, basically the statement is that this follows naturally from the Sugawara construction, because as you know, the Sugawara construction is kind of morally equivalent to looking at the Casimirs of the theory. And here the algebra has 2 Casimirs. One of them gives you the diffeomorphisms, and the other one gives you this notion of dual diffeomorphisms. Now, by looking at the algebra of these diffeomorphisms with their duals, you get at finite distance and for without boundary conditions and without even condition on the sign of these couplings P and Q, you get a double Witt algebra in each of these curvature and torsion sectors. And then in the flat limit, where Q and P are 0, these two dual diffeomorphism charges agree, and you recover a centerless BMS3 algebra. So the interpretation of this is that at finite distance, the current algebra contains already a huge amount of information. And this was also echoed this morning and explained a bit in the talk of Daniel. And so here, this construction, which reveals this double VIT or BMS algebra at finite distance, is very specific to the first order formulation and to the fact that you have added terms to the Lagrangian. So this kind of motivates us now to add similar terms and to do a first order formulation in 4 dimensions. Now, what happens in 4 dimensions is that you can add a natural term to the Einstein-Cartan Lagrangian, and this term is a topological term known in the literature as the Holst term. So you consider this first order Lagrangian for 4-dimensional gravity, E wedge F. The potential is E wedge delta omega. And now you can just use a very simple decomposition of the fields. So capital E.
Marc, can I just cut you? I'm very sorry, I made a big mistake. You have a full hour for a talk, so 5 minutes, no need to rush. Sorry about that.
No, I was speeding up, but I realized.
Sorry, no need to rush.
Okay, cool. Okay, so great. So to decompose this, so the potential here, E wedge delta omega in this form, it's not manifest that we have this decomposition that I talked about on the previous slide. So it's not manifest that this potential is the sum of the canonical GR or ADM potential plus a corner contribution. To make this manifest, we have to kind of properly decompose these fields. And this decomposition is done using the internal normal. Using this internal normal, you can decompose the 2 form in this way. So there is a, if you want, the epsilon piece is a rotation piece, and the En piece is a boost piece. You can also decompose the connection in terms of the spin connection gamma, preserving the tetrad, and the extrinsic curvature K. Once you plug these decompositions in the symplectic potential, you get on shell and up to a total variation that the potential is indeed a bulk piece and a corner contribution. So given here in blue and in red. Now, it's easy to convince ourselves that the bulk piece is indeed the canonical GR piece. This is just a simple rewriting, introducing this momentum aspect Pi, capital Pi. We get that on shell, this Einstein-Cartan symplectic potential is the GR one plus a corner contribution. So here we see that this topological term that we have added in the Lagrangian, so in the bulk Lagrangian, has actually been pushed to the corner. And it's pushed to the corner because essentially of this equality here, that on shell, when omega is the spin connection, this contribution to the symplectic potential is a total derivative, is a corner term. Now, again, this has implications for the theory because it has different charges and different symmetry algebra than canonical GR in metric variables. So if you look at the diffeomorphism constraint, again, we get a bulk piece and a boundary piece, which is the charge. The bulk piece is the familiar diff constraint, which is now written as a conservation of this 4 momentum aspect, Pi. And the charge is the usual first order charge for diffeomorphisms. So psi omega times E. And notice that because we have included this topological contribution proportional to beta, this diffeomorphism charge contains this so-called magnetic piece. And this kind of diffeomorphism charge was studied recently by this list of people. Now, because we have internal Lorentz transformations, we also get a constraint and a charge associated to these symmetries of the theory. So the constraint is the usual Gauss constraint. Covariant derivative of E is vanishing. And the charge associated to this symmetry are the Lorentz charges. And notice here that these Lorentz charges, they have, again, if we compute the algebra of these charges without actually thinking about how E is defined, we get the usual result that H alpha with H beta is H of the bracket alpha beta. But notice that here in this Lorentz algebra, the boosts and the rotations are both represented because we have introduced this beta piece. You see that if beta is 0, this Lorentz algebra has only a boost piece and no rotation piece. So introducing this parameter beta gives you access to the entirety of these Lorentz charges on the boundary. So this result tells us that the corner symmetry algebra of the of the ECH, the Einstein-Cartan formulation with the Holst term. So Einstein-Cartan-Holst contains the diff S piece and an ultra-local SL2C algebra. So one SL2C algebra per point on the surface. Now, why is this result important? Because essentially now that we have, if you allow me to just go back to the previous slide, now that we understand this split of the symplectic potential of the first order formulation between this universal bulk contribution and the corner contribution, we can focus on the corner contribution in red here and ask what type of physical information it encodes. So now I go here to see what information it encodes. And it encodes, as you will see, information about discreteness of geometry at the corner. So to see this, we have to study more precisely the tangential metric at the corner. So this is done by considering the tangential frame, so EIA. So I is a 4-dimensional index, A is a 2D index on the corner to sphere. This has 6 degrees of freedom, and it's convenient to decompose these 6 degrees of freedom in terms of 3 quantities. So one thing you could call a spin operator, SI, is just a wedge product of the tetrads. Then the tangential metric, internal product of EA, EB, and a component which is a twist angle, because it turns out that the spin operator and the tangential metric don't uniquely correspond to a given frame field. And now with this corner symplectic structure that we had written before, you can compute the algebra of this tangential metric, and you find that this algebra of the tangential metric is an SL2R algebra. And so this SL2R structure, or the non-commutativity of the tangential metric, is controlled precisely by the presence of this non-vanishing topological contribution measured by this parameter beta. So this is the SL2R algebra written here. Now what is important is that you see that we have rewritten the tangential frame in terms of the spin operator, the tangential metric, and this extra ambiguity angle theta. So there is an extra degree of freedom here. So the counting is consistent. It's really 6 equals 7 minus 1, because there is a geometric balance relation between 2 quantities. On the one hand, you have an SU2 Casimir, which is the square of the spin operator. So you can check that the spin operator forms an SU2, a rotation algebra. And then there is a Casimir of the SL2R representation. And it turns out that the Casimir of this SL2R algebra is given by the area element Q, or the square of the area element. And when we compute this, we find a geometrical balance relation relating the SU2 Casimir and the SL2R Casimir via this topological parameter beta. Now, this tells us an important information because since this corner is a space-like surface, we can actually look at the sign of the SL2R Casimir, which is given by the sign of the determinant of the metric Q. And this sign tells us that the SL2R representations, which are picked by this space-like corner S, is such that it is the discrete series of representation that appears. So this means that the area of these corners is quantized. So here, just from a purely continuum theory, without resorting to any discretization, any truncation, just studying the corner phase space of the first order Cartan formulation, but adding this topological term proportional to beta, we get that beta introduces, if you want, a gap in the corner theory. And this is a gap in the area. So the area becomes quantized because of the presence of this parameter. So this gives a notion of quantum geometry, if you want, to this, assigns a notion of quantum geometry to these corners. Then there is some extra structure, which I don't want to detail because I will not present too much the quantization of this here, but in the forthcoming paper, we give a precise construction of the quantum theory for this metric at the corner. And this relies heavily on the fact that the corner frame, now that it's available in the corner symplectic structure, provides you a complex structure on the boundary. So now what we have, if we go back to our table and complete it, we see that we have these kind of examples of 4 different formulations of the same theory, but these different formulations reveal different facets, different aspects of the corner symmetry algebra. So this kind of naturally asks the question of what happens if we go towards the bottom and if we go towards the right, what do we get? What is the maximal possible enlargement of this corner symmetry algebra? What is the physical information encoded in these extra components of the corner symmetry algebra? And what are the corresponding formulations of 4D gravity? Now, as I said, the goal of this to go further is to actually try to quantize these corner symmetry algebras. Because the idea is that quantizing the corner symmetry algebra gives you essentially the elementary building blocks of your theory of quantum gravity at finite distance, at least on your bounded region. And so the goal here is to, at least for future work, is to try to make sense and to give explicitly representations in the continuum of this corner symmetry algebra, which, as we have seen, has this universal contribution, which is diff S, and as a semi-direct sum with some ultra-local internal algebra. So typically here we have seen there is SL2C and also SL2R. But now what is important to notice here is that, so first of all, you notice that in 4 dimensions, there is a complicated piece to this algebra, which is diffeomorphisms of the two spheres. But there was recent work by Pena studying representations and characters of diff S2. And there's also, I think, forthcoming work by Laurent and William and Anthony and Moussavian also, studying representations of diff S2. So this doesn't seem like a too unreasonable prospect. But the most important thing is that, as we have already argued here, by looking at the SL2R Casimir, given by the tangential metric, and the SU2 Casimir, given by this spin operator at the corner, they are actually related and related together to the metric at the corner, Q, and related via this topological parameter beta. Now, just by working out some algebra, we can also show that the two SL2C Casimirs, so the Casimirs related to these internal Lorentz charges at the corner, these two Casimirs are also related to the area element, to the squared area element Q, and also related via this parameter beta. So this means that we have to find a way to quantize this corner symmetry algebra. But in this quantization, there is an important information. The important information is that the internal part of this symmetry algebra has all its Casimirs, which are related to the area element on the sphere. And now, as we have shown, in this formulation of gravity, where we include this topological term, this area element on the sphere is discretized. So, so the hope is that this discretization of the measure on the sphere can help us actually construct proper representations of this corner symmetry algebra. Now, if this is not doable in the continuum, I kind of try to argue in the beginning of the talk that there are many tools that have been developed recently to study kind of the quantization of this type of algebras. And this is, for example, what has happened for the past 20 years in approaches like loop quantum gravity. And you can kind of think that loop quantum gravity, in a sense, provides a very coarse, a very kind of brutal truncation of these degrees of freedom that are present at the corner. So, because you see these corner symmetry algebras, they are ultra-local algebras defined for every point at the corner, but you can actually think of discretizing these ultra-local algebras and making them into global algebras. For example, by taking smearings of the parameters of the ultra-local algebra as being piecewise constant on the surface. And if you do this, you get pictures which are very close to what has been the work that has been carried out in approaches like loop quantum gravity, with the only difference that so far, I would say that in loop quantum gravity, people have focused kind of exclusively on this SU2 and the Lorentz component of the symmetry algebra. People have kind of, in a sense, neglected and forgot to look at what happens with this SL2R component, which has to do with the tangential metric. And also diffeomorphisms are treated in a slightly different way. But at least it kind of shows that this is one kind of, this formulation of quantum gravity, which we have been developing, is kind of a singular limit of the project of looking in full generality at representation theory of this corner symmetry algebra. So it kind of also gives us this prospect of generalizing this and understanding in full generality the representation theory of this corner symmetry algebra. Now, I just go briefly through the last topic of the talk, and the last topic is that of edge modes. And so edge modes, we can ask what's the reason to introduce edge modes in a theory of gravity or in a gauge theory. And the reason is actually what brought us here in the first place, namely the observation that boundaries break gauge invariance in a gauge theory. Now, when we are facing this, we can, one possibility is to try to restore gauge invariance by actually suppressing the charges. And this we understand also in light of the decomposition that I have given, because as we have shown, any formulation, you can write the symplectic potential as a universal contribution and always a corner piece. And this corner piece is typically responsible for the appearance of new charges on the boundary. And these are the charges which, if they are not zero, this is the statement that the boundary breaks gauge invariance associated with this symmetry. So what you can do is introduce by hand, if you think that these corner terms are ambiguous, you can actually remove these corner terms and thereby remove these charges. But maybe this is not something which is which we really want to do, because as I try to argue, if we want to conceive and build the theory of quantum gravity from the quantization of these quasi-local symmetry algebras, what we want to do is have the largest possible algebra and more quantum numbers available on the boundary from which we can reconstruct the bulk theory. So I don't think we want to actually remove these charges. So one way to do so is to actually precisely introduce edge modes, because the role of edge modes is to precisely, in a sense, have the best of both worlds. So you can have restore gauge invariance at the corner, at the boundary, but at the same time have non-trivial symmetry charges. So that's one of the motivations. The other motivation is that the edge modes, they actually give you important information for how to do operations such as gluing, splitting, and coarse graining of subregions. If I depict this very schematically, thinking of the partition function or the path integral, for example, you can think of the partition function, for example, defined on the bottom left here for a manifold which is M union M bar. And you can think that you have some Wilson loops in this theory. And of course, if you want to split this at the location, the boundary of the manifold where you have split your theory in two, you have kind of open ends of Wilson lines that end. And so these Wilson lines, they end precisely at charges. And this is, if you want an information that you have to keep track of, if you want to allow these Wilson lines to exist and to be anchored on the boundary. And you also have to keep track of this information if you want to glue back the two regions together. So this is something which is familiar and can be explicitly realized, for example, in Chern-Simons theory. But of course, what we want to go towards is kind of a gravitational version of this picture. And also what happens, we see schematically here, is that if we split the path integral into these two regions, M and M bar, and then perform a trace, and compute, for example, a reduced density matrix by tracing over one of the regions, what we will get, and this has been illustrated in different examples. You can illustrate this in Chern-Simons theory, but also now we have an understanding of this in Maxwell theory. You see that the partition function does not actually factorize, because once you split the theory into halves and you trace over one of the two halves, you don't get the partition function for only the region M, but you get something residual coming from the region M bar. And this is, of course, nothing but the boundary theory induced by the edge modes living on the boundary. And this typically has contributions to it computes as a factor in the reduced partition function. And if you compute things such as, for example, entanglement entropy, by defining subsystems, you will pick up and measure the contribution of these edge modes. So there's been a lot of work by people trying to define subsystems in computations of entanglement entropy, because as you know, definition of entanglement entropy relies on the ability to factorize the Hilbert space. So here now I'm talking about a spatial setup. So you have a spatial region sigma and the complement sigma bar. And to compute entanglement entropy, you have to factorize the Hilbert space between sigma and sigma bar. But this factorization of the Hilbert space, although it can be kind of defined, but there are even subtleties in the case of a scalar field. In the case of a gauge theory, and more specifically gravity, the Hilbert space, of course, does not factorize. You can achieve factorizability of the Hilbert space if you precisely keep track of these degrees of freedom on which Wilson lines can be anchored at the boundary. And these are the edge modes which you want to introduce to enlarge the Hilbert space. So this is just a bit of conceptual motivation, but the more technical part, the precise way in which you can introduce these edge modes. So there's been kind of many different kind of definitions and ways to do this. So, so here the way I want to introduce them, just schematically to give the idea, is to introduce the notion of an extended potential. So the notion of the extended potential is that you can take the initial symplectic potential of your theory, but now we have shown that the symplectic potential of the theory, you can unambiguously ask what is the corner contribution to the symplectic potential, so theta s. Now you want to take this corner contribution of the symplectic potential and introduce two new ingredients on this corner symplectic potential. The first thing is that you can introduce independent fields on the corner, fields which are independent from the bulk fields. And we will see in a minute how these independent fields glue with the bulk fields. And you can think of these kind of independent fields at the corner as kind of, you will see in a minute, as kind of a dressing of the fields coming from the bulk. So this is a bit reminiscent of this dressing field method that has been also introduced. And also maybe this remains to be proven more rigorously, but of the kind of dressings that has appeared in this infrared triangle story. And now the second part to construct this extended potential is to replace the variation delta in the corner symplectic potential by delta plus this chi minus 1 delta chi, which you can see is a flat connection in field space, and where chi is an element of the group of your boundary symmetries. So here I'm still in the case of first order tetrad gravity. So as we have shown on the boundary, you have the ability to do these SL2C transformations and also these SL2R transformations on the tangent component of the metric or the frame field. And you can think of this as being like a choice of gauge frame on the corner. Now, once you have this extended symplectic potential, what this realizes for you is two things. First, now if you contract a gauge transformation in the symplectic structure coming from this extended potential, so now you have an extended symplectic structure, you contract a gauge transformation in this extended symplectic structure, and you get a generator which has a bulk piece and a boundary piece. Now the bulk piece is, as usual, the bulk first class constraint, for example, the Gauss law. If you look at internal gauge transformations delta alpha in tetrad gravity. But now the corner component, instead of being something that breaks gauge invariance, is you can understand it as a corner or a boundary equation of motion. And this boundary equation of motion is precisely enforcing a continuity condition or a matching condition between the fields which were living in the bulk and the fields which you have introduced as the corner edge modes. So this continuity you see is relating the bulk fields on the left to the bold fields on the right, which live at the corner. And this matching is via this the action of this Lie algebra element acting on the indices. So you have SL2C transformations for the internal transformations, and to match the frame, you have an SL2C transformation and also an SL2R transformation. So because once you act with these gauge transformations in the symplectic structure, you get two equations of motion. You have restored gauge invariance in this sense. But now, because you have introduced extra fields at the corner, you have also the possibility to act with a symmetry, which is only acting on the edge modes, on these independent bold fields which live at the corner. And the symmetry does not act on the initial bulk fields of the theory. And now once you contract such a transformation in the symplectic structure, you get a charge which is by construction supported only at the corner and which is gauge invariant. So this is, in short, to summarize the statement that once you introduce such a dressing of the symplectic potential with independent fields at the corner and these group elements which are gauge frames, you restore gauge invariance and you have at the same time non-trivial symmetry charges. And now to illustrate how this kind of fits with the picture that I try to introduce here, we can actually realize that there is an underlying nice geometrical interpretation to this data that we have seen is assigned to the corner region in first order tetrad gravity. And again, this geometrical interpretation is kind of, I think, nicely something which has been studied in the past 10 years or even more. And it has to do with something which is now known as twisted geometries. And these twisted geometries, as introduced by Laurent and Simone, were themselves, in fact, a generalization of a notion of discrete geometry, which are called Reggie geometries. So as you know, Reggie geometries are a way to discretize general relativity in terms of length of little simplices. Now, these twisted geometries, what are they? They are just, if you want, a map between the data that you can assign to a subregion, so to the corner of a subregion, and some geometrical data. So this data is as follows. You have these spin operators that I introduced before. So in terms of the frame field at the corner, you can construct the spin operators capital S. You have little s, which is a representation of the corner metric. So this is essentially, if you want, like the area of these little building blocks, these little triangles here. And you have also this, this angle theta, which has appeared before, and this angle theta is known as the twist angle. So it's the angle which is a kind of choice of freedom in how you rotate these triangles when you match them.
You have a question, Marc, from Shaheen?
Yes.
And maybe I can wait until the end of the talk. And I'll ask.
I'm almost done. It's my last slide. So
okay.
Okay, thanks.
So, okay, so actually it was a general question. I was thinking what happens if we take the corner that you're computing the charges over to be the bifurcation surface of the black hole? Is it, do we expect to get something more specific? And so there's a related question. I was sort of confused how the algebras that you showed would be related to what Carlip has. And he has a general BMS tree for any black hole.
Yes,
so, maybe I should wait later.
Yeah, okay, thanks. Yeah, but I'm happy to discuss this. Okay. Yes, I'm almost done. So maybe I end with this geometric picture. So this is saying that, so before we try to argue that once we can find a criterion for asking, given a formulation of gravity, what is the corner symmetry algebra that we get? And then can we quantize this corner symmetry algebra? Can we build representations of this corner symmetry algebra and think of these representations as building blocks of a theory of quantum gravity? Then we argued that if we introduce this topological term into action, we get from the corner phase space that the area at this corner is actually discretized. And now here, this geometrical interpretation says that if you kind of allow yourself to do kind of an approximation, a truncation, where you kind of see this corner as being discretized. That's why I have represented them by little triangles here. So you can think of them as being, they don't have to be triangles, but they are kind of some polytopes or some geometrical building blocks. They can be faces of bubbles more generally, but it's easier to represent them as triangles. You can associate data to these triangles. So a triangle naturally has an area measured by S, and it has also a normal. And the normal S is measured by this spin operator. And the twist angle is the twist on how you kind of twist these two triangles with respect to one another. Now, of course, if you glue two regions together, if you glue these geometrical data of twisted geometries from a left region and a right region, there will be kind of like like when you build a manifold, there is a transition function, a group element relating data on the left and data on the right. And this data is exactly the data which I have introduced on the previous slide, thanks to the dressings by the edge modes. And in particular, you have an SL2C holonomy, which is rotating this internal vector, the spin operator from the left, mapping it to the spin operator on the right. So this is mapping the internal SL2C index, but then you also want to map and to match the metrics coming from the left and coming from the right. So because of this, you want to act with a transformation, which is mapping the frame field instead of mapping the spin operator. And you can show that this transformation is actually an area-preserving diffeomorphism or an SL2R transformation. And so this is this SL2R group element, which is acting on the tangential index of the frame field. And you can think of this data as coming precisely from the edge modes, because if you look again at this bulk to corner continuity condition, which you get as the boundary equation of motion from this dressed symplectic structure, this is saying that the bulk field is equal to the boundary field up to the action of this group element chi. But now if you try to map the left region with the right region, and sorry, here I have S and T, this should be left and right. I changed notation. So ES should be E left and ET should be E right, sorry. If you map the frame field or the metric from the left to the right, you see that this mapping is done up to an holonomy, which is an holonomy in SL2C and SL2R. So this is kind of motivating and explaining that there is kind of a semi-classical geometrical interpretation for this data that you can associate to these corners. And this semi-classical geometrical data, which has now been studied for, there's vast literature and a good understanding of what these geometries are. You can think of this as being the classical counterpart of these quantum geometry building blocks, which you want to kind of construct and characterize in this approach, where you quantize the corner symmetry algebras. So this is just again another kind of indication, an ingredient that there is notion of quantum geometry which appears once you start to quantizing these local finite distance corner symmetry algebras. And with this, I conclude. So just to summarize, we have shown that there is a rich amount of structure which is already accessible at a finite distance. So I have tried to illustrate this also on the example of this three-dimensional model with these dual diffeomorphisms. And then in four-dimensional gravity, you have argued that we can kind of understand this structure and what is going on if we use this split of the symplectic potential between a canonical universal bulk piece and a corner contribution. And this tells us, if we take this seriously, that different formulations of gravity reveal different, essentially different physics at the corner. And in particular, when applied to tetrad gravity with this extra topological term, this has naturally taken us towards the notion of quantum geometry. So this means that there is room, I think, for kind of merging ingredients that have been around for many time now in what we could call a quasi-local holographic formulation of quantum gravity. So even though full quantum gravity in 4 dimensions might not be completely holographic because it has degrees of freedom, so I don't expect it to work like in 3 dimensions, maybe there is a prospect to actually find a way by quantizing the symmetry algebras to have enough quantum numbers coming from this quantization to be able to somehow reconstruct up to some approximation or truncation what happens in the bulk of these regions and thereby construct a theory of quantum gravity. So to really achieve this, what we still need is to understand all possible enlargements of this corner symmetry algebra, maybe using this organizational principle, look at different formulations of gravity, see what it brings on the corner, and see what extra charges are added by these corner contributions. What we also have to understand is how central charges can appear at finite distance and what their role is. It's also desirable to try to now push and understand the quantization of these corner symmetry algebras. And I think that this can be achieved and is actually work in progress. Hopefully we can realize this completely in the continuum, which we are trying to do. And if not, if it's too complicated, we can maybe resort to discretizations or approximations. Then we want to eventually reconstruct the space itself from fusion of this corner data, and then talk about evolving boundaries, dynamics, and fluxes. And then maybe a last exciting prospect is to maybe try to see a matter as a defect of geometry. This is what happens, for example, in three-dimensional gravity, where one can show that data assigned to massive and spinning particles is actually corresponds to some precise deformation, typically a quantum group or a double deformation of the algebra of local symmetries, namely the current algebra of, for example, Poincaré in the flat case. So maybe the same thing is possible in 4 dimensions. And with this, I thank you for your attention. Thanks.
Thank you very much, Marc, for this very nice talk. As usual, I let you run too long, but so some quick questions for Marc, please. Maybe there was Shaheen, of course.
Yeah, so can we discuss the questions I asked? So what are the implications of this corner symmetries and the edge modes for black hole microstates?
I think it depends a bit on how you, at which level you ask this question. For example, I think one implication is that this tells you that at least in this formulation, if you include this topological term, you get that the area is the area of your surface is actually discretized. So this gives you kind of a natural
well, it is not natural in the sense that the entropy of black hole is independent of this beta. It depends only on Newton constant among the parameters of the theory.
That's true, but here, I mean, here so far there is also no, I mean, there is no complete relationship here between the area and between this parameter. Here, I'm not claiming that this parameter will actually appear in the spectrum. I know that this is what happens in kind of the traditional formulation of loop quantum gravity, for example, but here this is kind of this recovers some of the ingredients, but in a kind of radically different different perspectives. So I would not, I'm not so sure that the same thing would exactly happen.
Maybe for the, if I can,
please, Laurent.
Yeah, comment. I mean, you know, if you want to get an entropy, at some point you have to be able to count states, and then so the question is, what are you counting? And the representation states of these algebras are, you know, the proposal for what you are counting generically. And if you want to have a finite area, at some point you need an area gap. That is, otherwise, if you have a continuous spectra for the area, your counting is going to be infinite dimensional. So there's a lot of challenge ahead before, you know, you can realize that. But the core is to count the degrees of freedom.
And again, what you are telling us about the H modes and this other corner charges resembles a lot this membrane paradigm. Can you also comment on if you think there is any relation between the two?
Yes, but to be honest, I'm not so familiar with the membrane paradigm, so I don't want to say something that is wrong. But yeah, do you mind maybe what do you think is the
okay,
so basic.
Yeah, please.
Okay.
Maybe my suggestion is to keep this discussion. Maybe you can do it with Laurent and Marc later or privately, because we are running really.
Sure, of course.
I think it's really interesting, but let's keep the philosophical discussions or the interesting ones for private discussions. Okay. Very good. Can you unshare your screen, Marc?
Yeah, sure.
So that Cédric may.
Yeah. Okay. Thanks, everyone.
Thank you, Marc. Thanks a lot. Cédric, can you hear me?
Yes, can you hear me?
Hello, Cédric.
Hello.
Maybe you have to put the volume a bit louder. I'm not sure.
Oh, you.
No, it's okay. I think it's okay.
I'm not sure I know how to do that.
Okay, I can hear you. It seems okay. Just take it away.
Okay. And okay. Hello, everybody. I would like to thank the organizers for giving me this opportunity to talk and present some of latest work. So I will talk about boundary degrees of freedom and their link with asymptotic symmetries. And okay, the main focus of my talk here will be about generic soft charges, as we could call them. So I will look at quantities of this form here, which are defined on the boundary, or more precisely for me here at infinity. And well, the basic example will be this one. So the asymptotic value of the electric field, or the radial electric field. And this is the object that has been related to the soft theorems with word identities. But so if you just take this object or any kind of similar object living at the boundary, you could, so you have these questions that are coming naturally, especially if you want to go into the quantum theory, and you will ask, okay, if they are well defined as generators, okay, you obviously have the questions of conservation, but which will be reasonably easy for us. And also a related one is what could be the associated symmetries. So if you have something that is conserved, you expect an associated symmetry. The usual answer in all these studies with the soft charges, and actually the answer for this one will be that there are well-defined Hamiltonian generators when we can associate some form of asymptotic symmetry to them. So usually, okay, I do it the other way. I start from the asymptotic symmetry and I go to the Hamiltonian generator. But in this talk, we will go from the boundary quantity and try to look at the associated symmetries. So the work that I would like to present here is the fact that, well, it's possible to extend so the set of well-defined boundary generators. So I mean Hamiltonian generators. And the idea will be to use some form of boundary or asymptotic degrees of freedom. And it's based on work in progress with Carapet that should have been out. Well, but life got in the way. So during this talk, I will only use the Hamiltonian description, and I will use it on T equal constant hypersurfaces. And so it means that all the charges, all the asymptotic charges that I consider are defined at spatial infinity. The main point when we use the Hamiltonian structure, or the control that we have over our theory, comes from good control over this Hamiltonian structure. And at least it has to be well defined.
being well defined implies two conditions that will be central to all this analysis. The first one is that the symplectic structure of your theory has to be finite. It's required because you want a well-defined object, but it will also be needed if you want a finite kinetic term in your action. Requiring this, in general, will restrict the asymptotic behavior of your fields. This is the way you can impose this finiteness. And well, in higher dimension, it's reasonably easy to get. In 4D, you have, it's subtle. So you will have to impose some form of parity conditions on your asymptotic fields, but it can be done. In this talk, I will not focus on this particular condition. So I will assume that everything has been done in order to have a finite symplectic structure. As the example I will use are in 4D, it means that you have this parity condition lying around. I will not mention them mostly, but they are there. The second condition, which is the one I will use or around which this talk is based, is the fact that you want well-defined generators. What do I mean by that is just going back to the original Hamiltonian definition. When you have a symplectic structure and you have function, or here functional. So you want the differential on the field space, this dv here, the vertical differential. If you take differential of your functional, it should be exactly given by the symplectic structure to which you feed the associated transformation here ig. So the vector in field space, which is the transformation associated to your generator G. So this is the general statement for Hamiltonian theory. If you have a simple symplectic structure of this form with only a bulk term, you check easily that your variation of the generator should contain only a bulk term. It means that all the boundary terms that you would create via integration by part should be zero due to your asymptotic behavior, which is, so this condition in this form is the one introduced by Regé-Teitelboim. Why is this condition so important? It's actually the second point here, which guarantees that your Jacobi identity is valid. If you don't have, if you don't use well-defined generators, so if you don't restrict your functionals only to these generators, your Poisson structure, your Hamiltonian structure breaks down. So I will focus on this one, and we will see what happens when we want to study these asymptotic charges or conserved quantities. The first example I would like to go through is one that I've done with Marc. So we studied electromagnetism in 4 dimensions. And obviously, the expected boundary charge, conserved charge, is the one that I gave at the beginning. So a boundary charge, which is the radial part, the leading radial part of the electric field. So here you have the Hamiltonian action for electromagnetism, and so this density pi is the electric field. And I have imposed, well, usual asymptotic condition, and not explicitly written, you have extra parity condition lying around. So this is not the full set of asymptotic condition, but I will not need the other ones in the rest. So basically, what these charges, and you can easily check that they are conserved because the leading term of the electric field at infinity doesn't vary in time. If you choose the profile of this arbitrary function epsilon bar, you can pick up any spherical harmonic of ER, whatever you want. So basically, any value of pi r on the boundary is a conserved, any point-like value is a conserved quantity. So the question, is it a Hamiltonian generator? Like this, with the usual symplectic structure associated to electromagnetism, it doesn't work because our symplectic structure is only a bulk term. So a Hamiltonian generator needs a bulk term. So the solution here is to complete the generator with the bulk constraint, which is the Gauss constraint, and we extend the parameter epsilon bar into the bulk to get the gauge parameter epsilon multiplying the constraint. So completing this boundary term with a bulk term, we get a well-defined generator G, and obviously on shell, we recover only the boundary contribution that we were looking for. So B epsilon is related to a generator, which is a generator of a gauge symmetry, of an improper gauge symmetry. And we have been talking about this as asymptotic symmetries. So this is the usual picture. So it starts okay, but unfortunately, okay, obviously we want electromagnetism to be invariant on the Poincaré, and so we check, do we have well-defined Poincaré generators in this setup? And it's not possible, well, it's difficult. We will see what we have to do, but with the symplectic structure, the usual symplectic structure, it's impossible to have well-defined Poincaré generators and non-trivial charges B epsilon, as I wrote before. The problem is that under boosts, so if you take a generic boost here, so xi perp, which is a linear combination of your space variables, a boost will rotate this leading electric field with the radial components of the potential, the asymptotic contribution. The explicit transformation are here. So you see that the boost acting on this pi bar r will pick up something, a contribution coming from the leading term in the potential AR. So if we act with a boost on these charges, the one that we studied before, built from the electric field, so the electric soft charges somehow, we build a new quantity, which is here. And if the Poincaré generators are well defined, nicely behaved, and our new generators P are also, if we complete them with the bulk term, well defined and nicely behaved, the result here should also be well defined somehow with your theory, in order for our theory to make sense. So it means that we need Hamiltonian generators of this form. So we start with asymptotic soft charges built from the electric field, and we see that if we want them, we also need soft charges made out of A bar R, again with an arbitrary function in front of A bar R. The only case where this doesn't happen is if we only look at the ones corresponding to epsilon constant, which would be only the electric charge. But if we want all of them, all the non-trivial ones, we also need the non-trivial charges built out of the potential AR. However, while we were able to complete the other ones with bulk constraints, here we don't have anything left. The bulk constraint goes with pi r. The generator containing A bar R at the boundary should also contain some form. If we want to add a bulk term, it should be some form of constraint, but we have nothing available. So we have a problem because this guy cannot be upgraded to a well-defined Hamiltonian generator. So here, what it tells us is that our Poincaré generators, and in particular, our boost generators, are not well-defined. So you have, and you can also view it as an integrability problem. So you are stuck somehow. The solution that we found is to add a boundary term to the symplectic structure. More precisely, so we added a new asymptotic field, kappa, which plays the role of the canonical conjugate to A bar R on the boundary. So it's a new degree of freedom that we added to the system, and we extended the symplectic structure like this. So you have the bulk term, which is the usual one, and you have a boundary term here, where we added a new momentum, boundary momentum for A R. If you do that, then basically you are promoting this expression that we were looking at to a Hamiltonian generator. The associated transformation is easily computed, and it's just a shift of this boundary momentum for AR. So we have, so this way it plays the role of the boundary momentum. And if you have this extended symplectic structure, you can check and show that also the boost generators, so the problem that I mentioned concerning the boost generators is solved, and you can also introduce proper generators for the transformation. You put everything together and you get this action for electromagnetism. So you have, so this first term and all the bulk term basically, so the first one and the last two are the original action, and we added so a boundary term to the symplectic structure, which means a boundary term to the kinetic term, which is here with a new momentum. For A bar R, we have this action and the corresponding asymptotic charges that are written here, or at least the Hamiltonian generators, with so the expected radial electric field, as at least its asymptotic value, and the second one that is needed for Poincare invariance, which is the asymptotic value of A bar R here. So the key point in this analysis was the introduction of this new boundary momentum. But if we were kind of forced to do it for electromagnetism, could we also use the same idea in other contexts where we are not forced to do it? In some sense, in the electromagnetic case here, our solution was minimal. So we introduced momentum, a boundary momentum for A bar R only. We could have added the same object for, or similar object for other asymptotic fields. So the question would be, what happens if we do the same, but when it's not necessarily needed? The consequence is that we will have other asymptotic quantities that will become Hamiltonian, proper Hamiltonian generators. So to show you an application in one example where it's more drastic, maybe, I will use the 4D scalar fields masses here. So you have the Hamiltonian action, and I will take reasonable asymptotic conditions. Again, if you want a finite kinetic term, you have to impose parity conditions on the leading term, but I will not, okay, they are around. You have a look, and easily one shows that asymptotically these asymptotic contributions will be preserved in time. It means that we can define asymptotic conserved quantities as before, but instead of being the radial leading contribution of the electric field, it could be here the leading contribution to phi and the leading contribution to its momentum pi. And again, I smear them with arbitrary functions on the sphere. And okay, I build soft charges in this case. Obviously, they are not Hamiltonian generators. I have the same problem as before. My symplectic structure is only a bulk term. So if I take a variation of this boundary integral, it's impossible to relate them just to this symplectic structure here. We've, however, seen a solution to this problem in the electromagnetic case, and then we can go on here and use the same idea and introduce conjugate variables, but to this asymptotic field phi bar and pi bar. And in this case, so what we get is a symplectic, an extended symplectic structure of this form. The result is as expected, and our conserved or our soft charges here are promoted. There are now Hamiltonian generators, and they generate shifts in our new boundary fields, kappa bar and pi and theta bar here. You could ask yourself, does this break anything? So I have changed the symplectic structure. My original theory was Poincaré invariant. You can check that everything is fine in the original one. Do I break something in the process? Mostly the answer is no. And in this case, you can check that Poincaré survives. So you get a new action that is also Poincaré invariant. So you need only a subset of the generators will be extendable. The condition being that the associated transformation of the boundary field should be internal somehow. So on the transformation of the asymptotic field should depend on the asymptotic field only. If you have that, you can, so the generator can be extended and to this new symplectic form. And you have, so we do the same. We had the corresponding kinetic term to the action, and we have an extended action here, for which these soft charges are proper Hamiltonian symmetry generators. So I call this the level 0 because we did it as a leading term. But if you study the asymptotic equations of motion, well, you see that you can also construct conserved quantities at the subleading term. So build out of phi 1 and pi 1, you just have to correct to take into account their time evolution. But again, you build subleading soft charges. Again, they are a priori not Hamiltonian, but if you agree to add canonical conjugates on the boundary, so we had the previous ones conjugated to pi bar and phi bar, and we'd add new ones going with pi 1 and phi 1. Well, it extends without too much problem, and we have the following action. So you have the original bulk action, which is here, and you have the boundary kinetic term, where I added momentas for all of the fields. And you also have to add some form of boundary term to the Hamiltonian, which is coming from the fact that these are not exactly conserved quantities.
Sorry, Cédric, you have 2 minutes or something like that to conclude.
Okay, I'll go. I was expecting that. So you build symmetry. By completing the action like this, you can build symmetry generators or Hamiltonian generators associated to these subleading soft charges. And you can, okay, obviously you see it, you can go further and further. So if you continue expanding your fields in a power series of 1 over r, you can continue the work here. It looks a little ad hoc as a construction, and so there are 2 questions coming with this. Is we don't have any gauge theory here. It's only a scalar field, and I'm only adding boundary degrees of freedom. So there there's this question: is it can it be viewed as some form of reduced phase space, as a gauge-fixed version of a bigger gauge theory, where these asymptotic charges are generators of asymptotic symmetries? The answer is yes. So we did it for electromagnetism. You can extend the theory again, and the boundary charge that the new one that we had that was needed for the Poincare invariance of the theory could be extended with a bulk term, and you see that basically the new charge is associated to improper gauge transformation of the potential A0 that we usually don't include. So the canonical pair pi0 and A0 is usually not included in our Hamiltonian description. So if you bring it back, you can view these new symmetries as asymptotic symmetries of A0. What is done here is that you can do the same for these new symmetry generators. So the soft charges that you could build out of all the leading, subleading fields appearing in the scalar field, you can also promote them. So you extend the theory by adding gauge invariance, and these conserved quantities will be associated to asymptotic symmetries. So this is the action, and I will then end. So if you add asymptotic degrees of freedom, and well, it looks ad hoc, but for electromagnetism, it's mandatory. If you don't do that, you don't have soft charges and Poincare invariance. So this is the only way we found to make it work. If you do that, you can promote arbitrary soft expressions to well-defined Hamiltonian generators, and you can also do that for subleading contribution. You can go down in the expansion easily, especially if you have a linear theory. And okay, I've not shown you, but these new asymptotic degrees of freedom, they can be viewed as asymptotic values of gauge fields. So basically, you add in the bulk new pure gauge canonical pairs, and these boundary fields that we added will be asymptotic values of these bulk gauge fields. And well, the last point I've not shown, but there is a very surprising link between with the jet space formulation, is that the new fields that you add in the bulk are the various fields that you would have in the jet space. So you, for phi, you add, for instance, phi I, which will be the first derivatives, and pi, you add pi I, which will be on shell, also the first derivative of the momentas. And when you ask these new fields, you impose the constraints that these new fields should be related to phi and pi. These first class constraints will generate the symmetry transformations that you want here. And if you extend, you go down into the 1/r expansion on the jet space formulation. You add more and more layers. So instead of taking only the first derivative, you add the second one, and etc.
Okay.
Yeah, I will stop here.
Thank you very much, Cédric, for this interesting conceptual talk about these problems. I would have questions on jet space and also on the link with Vadia's thesis of your introduction of the momenta.
I expected that.
Yeah, but let's do that in private at some stage. That would be better. There's one quick question from Ricardo Troncoso, so let's have him.
Nice talk, Cedric. Can you hear me?
Yes. Hello, Ricardo. It's been a long time.
I'm really impressed about what you did for the scalar field. So what you did was for the massless case, right?
Yes.
So one question, the charges that you proposed, are they somehow related for the zero mode, at least with the shift symmetry of the scalar field, that this global symmetry that the scalar field has?
That you can shift it by a constant. Phi goes to phi plus a constant, and it's a symmetry of the action.
Yeah.
Or the zero mode or something like this?
Well, the zero mode should do that. The zero mode of no, they don't.
Oh, I see.
Because the symmetries act on these new dual variables. Where are they?
Because I had a comment, but I'm afraid that because of the former reply, it won't work. I mean, a naive approach to try to tackle the case of the massless scalar field would be to dualizing it. Because I mean, if you dualize the scalar field and you write it as a true form,
yeah, we did
and
that.
then if you proceeded, like for electromagnetism, for sure, you would succeed. But I'm afraid that the charges you would find won't be the same, because if so, the zero mode would have appeared. You see?
No, you could. Okay, it works. So we did that with Marc also and studied the two-form description, and it's extremely similar to the electromagnetic case. The ideas are the same. The problems, well, are the same and bigger because you have a two-form and not a one-form. But the ideas are the same. You also have to add boundary degrees of freedom, and you can build charges. Okay, do they get information on the zero mode? I guess not. I'm not sure. I would have to check, but probably not because of the.
I see. So in summary, it's not that obvious that the charges that you propose will be those that would be obtained from dualizing the scalar field. But well, it's an open question.
No, the zero mode not, but the others. So if you take epsilon, which is not a constant, but you give it a profile. If you go in higher spherical harmonics, you can get more information. And those should be the same as the one in the two form.
I see. Thank you very much, Cédric.
You're welcome.
Thank you, both of you. I think we have to continue. Could you unshare your screen, Cédric? And
I find the option.
Very sorry to everybody. There will be no coffee break whatsoever, which means that I have to buy all of you coffee.
Stop share. Here.
So I suggest we just continue immediately with Francesco's talk and maybe grab a quick coffee in between. Sorry about that. Francesco.
Okay, can you hear me? Can you see me?
Very good, yes.
Okay, I should share the screen. How do
yes, can you do it? You should push the button below. Are you allowed to?
I don't think I'm allowed to because I don't see any button to do that.
Let's see if I have to give you permission. Let me just make you co-host if something, and then let's see if it works. Can you now do something?
Wait a second. And where is the button?
Usually at the bottom of your screen is a share screen button where you have unmute, mute, stop video. There is
okay, I don't see any of this button video.
So you have to see the full control screen of the Zoom application. Do you have that?
Yes. Okay.
And so if you wiggle it around, or maybe what you can do is do the view mode not in full screen, and then maybe you can see the commands better, because sometimes you have to go up to the top of your screen to see that if you're in full screen visual mode.
Okay, now I think I can do that. Can you see my screen?
Just give it a second to, not yet, but you pushed share screen?
Yes.
Yeah, very good, and it comes. Okay, very good, very good.
Okay, sorry for that.
No problem at all.
Okay.
So you have 30 minutes. If you can do it 25, I would be very grateful to you.
I hope I can. Try.
Yeah,
okay, so thank you for the invitation and thank you for having organized this very nice event. Okay, so today we'll talk about some recent work I've been doing in collaboration with Glenn and Martin about the notion of modular invariance in the context of finite temperature Casimir effect. So here is a, I think, okay, here's a plan of the talk. So we start by reviewing the two-dimensional Bose field living on a Euclidean torus background. So we start by giving some motivations. Then I will show how to compute the partition function of this theory on the torus. I will show how this partition function is actually modular invariant, and then I will comment about the physical and geometrical interpretation of this symmetry. Then I will switch to a more complicated model, namely the D+1 dimensional Bose field living on this partially compactified manifold, where we have T2, which is a torus, times RD-1. So I'm taking D-1 directions to be large and 2 to be compactified on a torus. I will show how to compute the partition function of such a manifold. And I will show how this partition function is actually modularly covariant, and it induces some kind of generalized high temperature, low temperature dualities. And then eventually I will switch to the case of electromagnetism, and in the context of a finite temperature Casimir effect. So I will comment about boundary conditions, gauge fixing, the constraint. I will go to the full reduced phase space, and I will show a reformulation of the theory in terms of a dual scalar field. And I will ask whether it is possible to talk about modular covariance also in electromagnetism. So let me start with the motivation. So of course, the first question is, why are we interested in partition functions? Well, partition functions are this kind of objects here. And if you're able to compute such an object, then you have access to very interesting quantities of the theory, namely the entropy, the free energy, and so on. So it's really a fundamental object to compute in QFT, in CFT, and so on. And of course, understanding the symmetries of Z can lead to non-trivial consequences. And in this talk, in particular, I will focus about modular symmetries. And one of the consequences of modular symmetries are the so-called high temperature, low temperature dualities, according to which, if you know theory at a certain regime, let's say the high temperature regime, then you automatically know the theory at the other regime, the low temperature regime in this case, and vice versa. So they're really a powerful tool. And also I should mention that modular transformations have been used widely in all areas in physics, like in QFT, in CFT. And these are some of the examples, like the Kramers-Vanier duality, according to which it is possible to determine exactly the 2D Ising model critical point. They have been used to derive the Kerr formula. And also in a slightly different context, they have been used to reproduce for the Sebian-Witten solution in N=2 super-Yaml theory. Okay. So let me start with the two-dimensional Bose field on a torus, which is defined by this very simple Euclidean action. So x2 here is my Euclidean time with periodicity beta, x1 is the spatial length with periodicity L, and then putting periodic boundary conditions on field phi, so that the underlying manifold over which the field phi lives is this torus here, which I will rather describe in the complex plane. So here I have a complex plane, I have two periods of omega1 and omega2. And I define the torus by identifying all the points in the complex plane that differ by an integer combination of omega1 and omega2. And this is what I mean by this relation here. And also I can introduce a modular parameter for the torus, which is the ratio between the two periods, omega1 and omega2. And it is a purely imaginary number, in this case, for a rectangular torus. Of course, I can introduce the Hamiltonian and the momentum using the n=0 Virasoro modes for this theory. And I call H prime the Hamiltonian because I'm actually excluding the zero mode contribution, which I have to take into account separately, as I will show in a few slides. And once we have these observables, we know we can compute the partition function of the theory, which is given by this expression. And you see that, of course, in this expression, it appears only the imaginary part of modular parameter tau, because this is the only one that we have. But if we consider instead what we call extended partition function, in the sense that we turn on a purely imaginary chemical potential for the momentum of the field P, then you see that the only effect on the partition function is to add a real part to the modular parameter. And the geometrical interpretation for this is that, is that we are actually switching from a rectangular torus like this one to a skewed torus just by adding a real part to the modular parameter, which is controlled by the parameter mu. Okay, if now you compute the partition function of this model, you can express it in terms of the Dedekind zeta function, which is defined in this way. And then, but this is still, this is not yet modular invariant, because we have to add zero mode contribution, which you can check. It is given just by a free particle, so that the full Hamiltonian is the Hamiltonian of a free particle plus h prime. And then the full partition function is expressed in terms of z prime just by multiplying it by 1 over the square root of the imaginary part of tau. Now you can check that this result, this z, is here fully modular invariant, in the sense that if I do a transformation of modular parameter like this, then the partition function is invariant. And in particular, of course, it is invariant under translations and under inversion symmetry. And this is the symmetry I'm going to be interested in, because it has a nice geometrical interpretation, in the sense that, so if I swap, so I have the thermal cycle and the spatial cycle, and if I swap them, so I go to this different manifold, then the partition function is invariant. It's equal on these two different manifolds. And the interpretation is that the theory at a certain temperature beta over L, or kind of reduced temperature beta over L, is related to the theory at inversely related temperature L over beta. And what I find nice about this construction is that by the properties of a CFT, everything will depend on the modular parameter, which is the ratio between two periods. And also the fact of having a Euclidean torus background, it imposes some powerful constraints on the operator content of the theory. Then I will switch to the d plus one dimensional massless scalar field, which is defined by this Euclidean action here. And I'm assuming that the field phi lives on this manifold, Rd minus 1 times T2. So I'm taking d minus 1 directions to be extended to be large, while two of them, including the Euclidean time xd plus 1, which has again periodicity beta, and just one spatial direction, xd, as periodicity L. So really the manifold is this one, Rd minus 1 times T2. And again, I can construct the Hamiltonian of the field given by this expression and the momentum of the field in the compact direction, PD. And of course, here I should mention that I'm actually working in Hamiltonian formalism, so that this big pi here is just the conjugate moment with respect to the field phi. And again, we can consider the extended partition function given by this expression. And the question we ask now is, what are the modular properties of this Z? So of course, to answer this question, the most straightforward way is to compute the partition function directly. And one way to do that, there are several ways. One of them is to use the Hamiltonian path integral formulation that in the end, it boils down to compute the zeta function associated to a certain operator, delta mu, which is just the Laplacian on this particular manifold, which has a component which is Rd minus 1, which is this component here. And then you have this Q the torus again. So this is the torus. And here again, we have omega 1 shifted by a real part controlled by mu. What I find interesting is the final result. So it is composed basically by two pieces. The first piece is a prefactor that depends only on the imaginary part of the modular parameter, which is tau2, times a function, which I call f, which is the so-called real analytic Eisenstein series given by this double sum. And why this result is interesting? This is interesting because the Eisenstein series is manifestly invariant under modular transformations, at least in the case in which d is greater than 1, so that the full modular behavior of the partition function is entirely controlled by the prefactor. And in fact, what you can show is that the partition function, actually the log of the partition function, is a modular form of weight d minus 1. So it transforms under modular transformation in this way. And again, in the case in which you have vanishing chemical potential, in the case in which you specialize to inversions, then the log of the partition function should satisfy this symmetry here, where tau2 is beta L. And the geometrical interpretation is now this one. So you can swap again the two cycles, so the thermal cycle and the spatial cycle. But the effect of swapping the cycles now is to get a prefactor, which is L over beta to the d minus 1, which is entirely due to the fact that we are having d minus 1 dimensions to be large. Indeed, in the case in which you take d equals to 1, you get again the full modular invariance of the partition function. So this symmetry implies what we call generalized high temperature, low temperature dualities. In particular, if you compute the log of the partition function at high temperature, it is going to be related to the log of the partition function at low temperatures by this formula. What you can show is that the partition function in the low temperature limit admits this expansion. You have, of course, a lot of other terms which are exponentially suppressed. And the leading contribution to this scales like 1 over L to D, and it is the usual Casimir contribution, which is entirely due to the fact that the spatial direction is small. And then here we have a subleading contribution on which I will comment later on. And while the high temperature regime of the partition function is given by this expansion here, where the leading term is the black body result, which scales like the volume of the system divided by beta to the D. And what is really nice that this Casimir contribution, once you apply the symmetry, maps entirely into the black body result and vice versa. So the large volume limit somehow is already contained in the small volume limit by this.
Francesco, just a moment. Gaston has a question. So.
Yes. Please.
Hey, hello. How are you doing? My question is about the phase transition. Do you expect some kind of phase transition, like a Hawking phase transition, when the temperature is 1 over L or something like that? I mean, yeah. This is at that point the prefactor becomes 1, so the partition function of the interchanging or not interchanging the thermal cycle just is the same. So, and this can be thought of as some exponential of a free energy or something like that. So I suppose that at this particular point, namely with beta is equal to L, you have a coexistence of the two phases, no? Right? The two free energies are the same. So do you expect some phase transition or not? That's my question.
So in order to talk about phase transitions, so here we have no interactions. We are considering really just a free field theory, and we're checking what are the high temperature and low temperature limits of this theory, which is so you don't have even a mass, you don't have a coupling constant, it's just a free theory. So I don't know whether you can talk about really phase transitions. The only parameter here is the temperature. These are the two regimes of the theory in the two temperature regimes, so the low temperature and the high temperature. And
still,
if you take, yes.
my question remains, even if you are thinking in that case, you can think of some phase transition happening at beta over L equal 1.
I think so. I think so, that in the case in which beta over L is equal to 1, maybe you have a phase transition. We still don't have any computation in this direction, but we would like to. Okay, maybe we can discuss later about this. But
okay, thank you very much.
Okay, now there is a subleading term in the low temperature expansion of the partition function, and you can trace it back, and you can show that actually this contribution is due, the subleading contribution is due to the ND term equals 0 term of the mode expansion. So you can really take the field, you expand it into modes, and the ND equals 0. So in the compact direction, it is responsible for this contribution here. And what is nice is that if you now compute the low temperature expansion of the entropy using this formula here, then you can show that the Casimir contribution drops out because it is linear in tau 2, and the leading contribution of the entropy is given by this equation here. And what is surprising is that it does not scale as the volume of the system, but somehow as its area, so by the volume divided by L. Okay, now the ground is ready to talk about electromagnetism. So I think a good starting point is to talk about the famous paper by Casimir, the seminal paper in 1948, in which he was computing the force between two metallic plates placed in vacuum. So this is the setup. There are two metallic plates separated by a certain distance d. Then I'm taking L to be much greater than d. This is the assumption of the Casimir computation. What he is showing is that indeed, there is a force, an attractive force between two plates, which the interpretation of this force is that it is entirely due to the fluctuations of the 0-point energy of the electromagnetic field. So now in this box, I've placed the black body result for the energy of both the electromagnetic field and that of a scalar field and the Casimir energies. What is immediate to notice is that you can actually guess the electromagnetic results just by taking the scalar field result and switching D to 2D. And also there is a nice paper in 1969 by Brown and McLean, which they were actually computing already the log of the partition function of electromagnetism in the Casimir setup. And they had shown that it satisfies this symmetry here, which reminds us a lot of what we were discussing in the previous slides. But again, the weird fact is that the imaginary part of the modular parameter here has this factor of 2. So all of this would suggest that electromagnetism in the Casimir setup is equivalently described by just a single periodic scalar field that lives somehow on the double volume. And the question is now, can we enhance this formula to full modular covariance? And in particular, how do we add the real part to the modular parameter? So a good starting point is to talk about boundary conditions in electromagnetism. So we know that on the metallic plates, the tangential component of the electric field should vanish, and the normal component of the magnetic field should vanish on the plates. If you translate these boundary conditions in terms of the conjugate variables A and pi, then it turns out that the parallel components of the field with respect to the plates should satisfy the Dirichlet condition on the plates. So they have to have these sign expansions here. While the three components of the field, so the components which are normal to the plates, they should satisfy Neumann conditions on the plate. So they have to have an expansion in terms of cosines, but Neumann conditions fix only the derivative of the field on the plates, not the field itself. So we have room for an additional zero mode, which it is interesting. The next step is to introduce a basis of polarization vectors, EE, EH, and the parallel, which are defined as long as k is different from 0. And then you can expand every field in momentum space along this basis, like this. And in particular, you can expand the canonical variables in this space, in this basis. And now if you try to solve the gauge condition, which I take to be the Coulomb gauge, and then if you solve the constraint, then it's not surprising that they're gonna kill the longitudinal components of the field along the E parallel. So the Hamiltonian is diagonal in these variables. So you can check that if you compute the Hamiltonian of electromagnetism, it is given by this simple mode expansion. And I'm calling this again H prime because I'm working with k different from 0. So again, I have to add by end the zero mode contribution. If I take it into account, so the k equals 0 mode, you can check that it is given by, again, by a free particle, so that the full Hamiltonian is just a Hamiltonian of a free particle plus H prime. So the full Hamiltonian in the reduced phase space is given by this equation. So we have two fields, the H field and the E fields. And what is different is that the E field has an additional zero mode, which reminds us about the Neumann boundary conditions. So this is a box that, to recap all the degrees of freedom in the reduced phase space. So we have three sectors. The first sector is for K3 different from 0. So we have the E modes and the H modes, and they satisfy these canonical Poisson brackets, while in the K3 equals 0 sector, we have only E modes, and they satisfy this kind of reduced Poisson brackets, while in the K equals 0 sector, we just have a free particle. So what we've shown so far is that electromagnetism with Casimir boundary conditions, plus the gauge fixing, plus having solved completely the constraint, is equivalent to the sum of two scalar fields. One is the E field, and the other one is the H field. And the E field should satisfy Neumann conditions on the plate, and the H field should satisfy Dirichlet conditions on the plate. So the electromagnetic field is really equal to a scalar field with Neumann conditions plus a scalar field with Dirichlet, as I just said. So, and the usual statement that polarization effects just double the number of modes can turn out to be inaccurate because it is trivially true in empty space, but in the case in which you have finite boundaries and the boundary conditions on these boundaries, you have to take care of all the details of the mode expansions and so on. What you can do next, you can glue the modes together in this way. So you can glue the E modes and the H modes in this way, both for phi and for pi, so that the full Hamiltonian can be expressed in this very simple equation, which is nothing but the Hamiltonian of a single scalar field with periodic boundary conditions in the x3 direction, because n3 now is an integer number. So the action of electromagnetism is further simplified to that of a single scalar field, but it has to satisfy periodic boundary conditions in the x3 direction over a length of 2d, not on d. And so this is somehow what we were expecting, what we wanted to show. So in the end, the electromagnetic field in this setup is equivalent to a dual scalar field with periodic boundary conditions in all directions, living on the double volume. And this is a geometrical interpretation of what we're doing. So we have the H modes, which satisfy the Reclay conditions on the plate. We have the E modes, which satisfy Neumann conditions on the plate, so they have cosines. And the sum of the two is equivalent to a single scalar field, phi, that has periodic preconditions in all directions, that lives on the double volume. So at some point I asked the question, can we enhance the full modular covariance, the symmetry found by Brown and McLay? And now we can answer this question because we can reformulate entirely the electromagnetic partition function in terms of that of a scalar field on this manifold here, R2 times T2 mu. We can just literally copy paste the result of the scalar field and substitute D with 2D. And the log of the partition function is again given in terms of the Eisenstein series. And in particular, it is a modular form of weight 2. And again, in the low temperature regime, you have this expansion here. So the first term is the Casimir contribution. And if you take the force coming from this contribution, you will have the original Casimir computation. You have this subleading term, which I will comment later on again. And while in the high temperature limit, you have the standard black body result. And the two of them are connected by the inversion symmetry. So again, if you compute the entropy in the low temperature limit by this formula, you see that the entropy, the leading contribution to the entropy, so the Casimir contribution drops out. And again, you have an entropy which scales like the area of the system and not like the volume. And the nice fact is that now we have a macroscopical interpretation for this term, because we know exactly that these terms, they come from the N3 equals 0 mode, that are just photons that propagate parallel to the plates. So these are the modes I'm talking about, that are parallel to the plates. So what we've done so far, we have mapped entirely the dynamics of the electromagnetic field in terms of that of a scalar field. In particular, we've shown that the Hamiltonian of the electromagnetic field is entirely mapped into the Hamiltonian of a scalar field living on the double volume. And we've seen that adding the momentum of the scalar field in the compact direction, we can achieve a full modular covariance. And the question is now, when we try to re-express back P3 in terms of the original electromagnetic variables, what is the observable that we get? One could naively guess that it is just given by the momentum of the electromagnetic field along the x3 direction, but this is too naive. In fact, okay, so for the dual scalar field, of course, P3 is just the usual generator of translations along the x3 direction, so it acts through the commutators in this way, so it is just a shift of the field in the x3 direction. While if you go to the picture in which you have two scalars, then you can show that P3 is given by this formula here. And you see that, again, it acts on the two fields by means of a shift in the x3 direction, but it also has an additional action, so it flips the polarization of the fields, both of the E field and of the H field. While if you try to express the original electromagnetic field, so AA, the spacetime components, you can show that they are related to the H and the E fields by this ugly non-local relation here. You can show again that P3 in terms of the original electromagnetic variables is given by this non-local expression, where you have square root of delta, minus delta, which is the Laplacian. What you can show is that if you now compute the spin angular momentum of the electromagnetic field in this setup, you can show that in the reduced space, it is given by this expression here, which is very similar to this one. The only difference is that now you have this square root of minus delta, which is the non-local contribution. So they're pretty much the same observable. Just you can think of this square root of minus delta as multiplying the momentum space by k. And this is the difference between the two observables. Of course, the action is very similar, and we've seen that it flips somehow the polarization. Okay, so now it is time for conclusions. We've shown that the partition function can be expressed in terms of the Eisenstein series. In particular, it is a modular form of weight d-1 for the d+1 dimensional scalar field. It induces some kind of interesting generalized high temperature, low temperature dualities. We've shown that the electromagnetic field in the Casimir setup can be described by two scalar fields, the E and H fields, satisfying Neumann and Reclay conditions, or just by a single dual scalar field with periodic boundary conditions living on a fictitious double volume. And of course, we can extend the notion of modular covariance also to electromagnetism in the Casimir setup. And you can do this all by turning on a chemical potential for the momentum along x3 of the dual scalar, or you can do this by turning on a chemical potential for what we can call adapted spin angular momentum for the electromagnetic field. These are some future directions of research. So the first is that, of course, we would like to extend the construction to more complicated gauge structures. And I invite you to see the next talk by Martin about it for linearized gravity. Of course, we also plan to extend it to the case of higher spin, to extend it to the case of free fermions. But here you have to be careful because you can have also anti-periodic boundary conditions, so that in the end you would have, I think, a twisted torus. And in the end, we would like to add interactions. So consider non-abelian gauge theories. So SUN gauge theory, in particular, these boundary conditions, which are relevant in QCD to describe confinement, they could be interesting to study. And of course, we would like to consider other geometries, which are slightly more complicated and carve the backgrounds. So black hole backgrounds and so on. And okay, I'm finished. Thanks.
Okay, thank you very much, Francesco. So there was already a talk, a question by Stefan. Maybe you can ask it now.
Yeah, hi, Francesco. Thanks for it. Very nice. I just have a basic question. So in 2 dimensions, modular invariance, as you said, imposes some constraints on the. It's not every 2D CFT is modular invariant, so it puts some constraints on the operator content. So in higher dimensions, is it the same thing? So for example, for the CFTs in the higher dimensions that we have in mind, are these CFTs, I don't know, super young Nielsen equals to 4, for example, are these theories modular invariance, for example? Is it trivial?
Strictly speaking, modular invariance is just a feature of 2-dimensional CFT.
But what I meant is the modular the thing with the C tau plus D times the.
You can have in higher dimension, you can have modular covariance.
Modular covariance, yes.
But this really depends on the fact that you have a piece of your manifold which is a torus. So you can take these d-1 directions as very large, and then you, as long as you have this component for the manifold, this T2 component. So if you impose periodic boundary conditions in these 2 directions, so the Euclidean time and 1 spatial direction, then you can talk about modular covariance, I think, for at least for any free field theory. This is what I think. I don't know
for example, if you take n equals to 4 super Young Mills and you put it on R2 times T2, is it modular covariant for free?
I don't know. I have never done this computation, to be honest. But I think modular transformations are important in n equal to super Young Mills theory, but the interpretation is kind of a bit different because the modular parameter there, it contains the coupling constant of the theory. So the theory is interacting, and also there is the theta angle. So the interpretation is quite different. I don't think the partition function of the theory is modular covariant or so on, but I don't know. Honestly, I have not yet done this computation. I think it is pretty hard.
Maybe, Stefan, can I point you to the paper by Shagulian on this, which talks about Young Mills? We have only done the Gaussian model, and this also answers, I think, Gaston's question, because if this Eisenstein series is real analytic, there is absolutely nothing in the partition function where anything diverges or any derivative of the thing diverges. So you really need to put interactions if you want to go beyond the free scalars that we have looked at. Right? But okay, let me, maybe Ankit has another question.
Thank you very much.
Yes. Yeah, so are you including the 0 modes in the partition function?
Sorry, can you please repeat?
Are you including the 0 modes in the partition function?
Yeah, I have to include the 0 mode. So in the 2-dimensional Bose field on a torus, I actually have to include the zero mode. And as I was showing at some point, you have to do it by hand. And it is just a free particle contribution to the Hamiltonian. And in this case, you see that just you take this partition function, you multiply it by 1 over square root of tau 2, and this adds the zero mode contribution. Then the full partition function is modular covariant. In higher dimensions, you can actually discard the zero modes, because in the large volume limit, zero mode in d+1 dimension will be different from 1. It's going to vanish. The contribution is very subleading. So you can forget about this, and still you have modular covariance in higher dimension. Also by discarding completely the zero mode. If you don't have any charge coupled to your system, because the zero mode is going to couple with the charge. Let's say if you put some charge distribution on the walls, on the boundaries, then the zero mode is going to play a role. Otherwise, you can just.
I thought there would be some logarithmic divergences and so on.
Okay, maybe
in +1 dimension there are no divergences. Here, so in the two-dimensional case, you have to take it into account in a separate way, because the spectrum of the zero mode is kind of different. So you have to perform the contribution of the partition function of the zero mode is kind of a different contribution. So it is just a prefactor here. You have to take into account very carefully, and sometimes it can lead to divergences, but you have to regularize. So it's quite complicated, but I think this is the most accepted result in the literature for the zero mode contribution, the square root of tau 2, at least in 2D case, the two-dimensional case.
I suggest you do this discussion.
One question.
Yeah, there was one question from Konstantinos Svetsos, I guess. It is.
Yeah. Yes, right.
Yes, hi.
Okay, so I think, if I remember correctly, you can play around with the sign of the Casimir force by including dielectrics. So my question is, I was wondering, in the picture with the torus, how would you do the appropriate modifications to include some sort of dielectric phenomenon in the case of when you make contact with electromagnetism? So this is one question. And the second is, if I remember correctly, the Eisenstein series, when the index is 2, has some anomaly under modular transformation. So I was wondering if this case arises in your analysis. Thank you.
Yeah, okay. So I will answer before to the second question and then to the first. So I will try to answer it. So the Eisenstein series, as I was telling, is given by this double sum here. So if you take S to be 1, so you take in the D = 1 case, this series is actually divergent. So you can not really talk about Eisenstein series this expression is divergent in the case in which S is equal to 1. It is formally equals to infinity. And this is why in the 2D case, you cannot really express the partition function in terms of the Eisenstein series. You have to take into account the Dedekind eta function, which is a different function. So you have somehow, in 2D, you have a different, I would like to call it phase transition, but it's not a phase transition. It's just that in 2D, you have to do the computation in another way, because you cannot use the Eisenstein series. And in particular, if you remove the absolute values here, and you take just the series without the absolute values, instead it converges. It is finite, but it is not absolutely convergent, of course. And then you cannot really switch. It is not modular invariant. It is a quasi-modular form. So in D = 2, you have to deal with quasi-modular forms, I think.
Okay, if I may say something, there might be a small confusion here between the real analytic Eisenstein series and the holomorphic ones. It's G2, and this is like G4. F2 is like G4, so there's no problem with this one with anomalies, I would say. This is really, yes, that's
Okay, that for the first question, then of course, if you want to consider something more realistic, then you cannot use the perfectly conducting plates, because of course this is an idealized model. You have to put some dielectric stuff on the boundary and to see how of course you can see how these new boundary conditions would modify your theory. And you can play, as you said, by putting something else on the plates, considering some real plates to some extent. Then you can reverse the sign of the Casimir force. You can do that. But I don't know what the effect of these new boundary conditions, taking into account the electrics, on the partition functions. We have not computed it. We just done the this very simple model, this super idealized model, and that's all.
Okay, maybe let's, sorry, Costas, let's maybe, so Shaheen had a question, let us.
Thank you for the nice talk. Actually, maybe it's related to the previous question. You consider just the Maxwell theory, but you can also add a theta term, FHF term, and this will change the boundary conditions without changing the bulk dynamics, right? And I was wondering how this theta term, in particular the theta parameter, appears in your partition function.
Well, I don't know, because I haven't done the computation, but of course you can add a boundary term which is controlled by
Oh, Francesco, we are losing you. At least I can hear you.
You don't have to include the momentum. And then you can, sorry, can you hear me?
Oh, yeah.
Okay. Okay, so I think my guess would be that the modular parameter would include also a contribution from the theta term. So it would be beta, L, and the theta term in the modular parameter. But this is just speculation for the moment, because I haven't done any computation yet about this. But my guess would be that, of course, in tau, there would be a part in which there is also the modular, the theta angle. Somehow.
Well, maybe we should discuss it later, but I think theta will, of course, appear in the partition function, but not in the tau. Tau would be exactly the same as what you have here. The Epstein zeta function has the room for introducing an extra phase, which I think that's where it appears. But we can discuss it later.
Oh, maybe. Yes.
With pleasure.
With pleasure.
Okay. Thank you, Shaheen. Ali, a quick question. Quick, please. Ali? Oh.
Do you hear me?
Yes.
Yes.
Okay, yes. This p hat that you had, you mentioned that at the same time it's a translation. It generates a translation and also a kind of duality transformation, right?
Yes.
So but the expression that you write is very complicated. I mean, square root delta doesn't mean anything. I mean, for me, I mean, in a space-time, it's very complicated. But can we write it really in terms of as the composition of the two generators, the duality transformation, the generator of duality combined with like a space translation, something like this? If we try to massage this equation to find something nicer a bit?
We've tried a lot. And the reason why I'm putting this expression here, which is quite ugly, is that we don't have any, at least any better expression for this P3 in this moment. But you see, it is quite complicated because it has this square root of minus delta once you put it in a coordinate space. But if you think about it, just in momentum space, it is just a multiplication by k. So in momentum space is much more nice. It's
yes,
much better.
that I understand, but I want to see it. I mean, as you show above, it generates translations and duality transformations. So it should be somehow related to the generator of electric magnetic duality and also.
Well, you know, I think if you want to do that, you have to introduce more potentials. If you introduce higher potentials, like in this potential formalism, you can get rid of this square root of delta. But basically, nevertheless, if you go back to the original variables, it's the same. Even the duality generators, if you write them as canonical generators, they will have this stuff as well. In the okay, the last question maybe from Charles.
Hi, thanks for the talk. I just wanted to know, so at the end you mentioned maybe applying this kind of techniques to the black hole. What could we learn? Because maybe I guess one of the idea would be to derive an area law. And what would be different, I guess, from the Hawking's calculation?
Well, this is, of course, a complicated question. Of course, the idea would be to use carved backgrounds like the Schwarzschild solution and black hole solution in general, and to see if there is still some contribution to the partition function that scales like the area. And in this case, it would be nice if it was the area so the event horizon area. But says what is nice about this is that it would be nice if we have an additional so if we have an interpretation of the degrees of freedom contributing to that part of the entropy. For the moment, we can just do very simple geometries like the one that I was considering, which is the Casimir geometry with just two parallel plates. And this is the best we can do because we know exactly what is the basis. We have a full understanding of the space. We can really trace back the contributions of the entropy to the mode expansion and so on. And I'm not completely sure that you can do that with other geometries and carve the backgrounds. So you should have, of course, should use some approximation technique or I don't know. We are looking forward to answer all these interesting questions.
But we really have to stop. I'm really sorry because, well, maybe you can get a bit of your answer from the next talk, but it will also be linearized. Okay, thank you very much, Francesco, for the nice talk.
Thanks.
Maybe can you unshare your screen so that you can.
Okay, I think now it is unshared.
And then Martin should try to share his screen. Maybe
I cannot share my screen because Francesco. Okay.
Yep.
Okay. Perfect.
So can you hear me and see the screen? No.
Yes.
Okay. So hello everyone, and thanks to the organizer to organize the event. So I will, as Francesco said, I will present how to compute the partition function of gravitational waves with Casimir boundary conditions, with Casimir-like boundary conditions for the gravitational fields. So first I will review some background about the linear gravity and the Hamiltonian formulation of it, and the setup, the geometrical setup of the Casimir effect. And then I will construct the map to two scale from the linear gravitational field to two scalar fields. And then, as Francesco showed, this allows to compute the partition function and to exhibit some properties of the modular properties of the partition function. So first, what is the dynamics of the polyfirst field? So it has this action with the Hamiltonian, which is this one, and there are two constraints, Hamiltonian constraints, which are these two ones. And they are, actually there are four constraints, and they generate gauge symmetries of the theory. And so the geometrical setup is the one is the interior of two infinitely extended plates, so as represented here. And on the plates at x3 equals 0 and x3 equal a3, I take as boundary conditions these ones. So HAB and H33 are Dirichlet, and HA3 is Neumann. And in the large directions XA, so X and Y, I take the fields to be periodic as usual when we deal with large directions. So we can expand the fields in the usual way. So the Dirichlet fields have signs in the X3 variables, and HA3 has cosines with these combinations for the momenta. And we have to notice that HA3 and pi A3 have entry equals 0 modes because they are are Neumann fields. So they can have n3 equals 0 modes. And the other thing to notice is that the infinite space, the correspondence rule that partial J gives ikj in Fourier space, which is the infinite space, which is valid in infinite space. This holds up to some I factors in this context, in the Hamiltonian and in the constraints. And so the Hamiltonian and the constraints are really easy to compute in Fourier space. And so now I can go to the map between the HMN, PyMN, and the scalar fields. And so first we have to introduce the TT, TLT, and LL components of the fields. And so this is done at fixed vector k, and so different from 0, as Francesco said. It is defined for k which is different from 0. And the Fourier components here is expanded in this polarization tensor basis for symmetric matrices. And this, the EIJ are matrices with given dependence on K, and they are exactly the same as in the infinite space decomposition of H made by Deezer, for example. And so after gauge fixing, which is equivalent to going to the reduced phase space, there are only two physical polarization remaining, which are the TT plus and TT times. So there it remains two polarization, and the dynamics are that of harmonic oscillators of frequency k squared, as expected from by analogy with the infinite space case. And so the scalar fields, the plus oscillators can be reorganized into a Dirichlet scalar field, exactly as in electromagnetism by analogy. So the plus here, the plus oscillators are analog to the E oscillators in electromagnetism. To the H oscillators, and the times oscillators, they form a Neumann scalar field like the E oscillators in electromagnetism. And phi times is Neumann because it is naturally associated with cosines, and it has also n3 equals 0 modes, and this comes from the Fourier expansion of HA3, which has n3 equals 0 mode. And next, because of the geometry, we can we can merge these two scalar fields into a single scalar field, which is periodic over the double interval minus L3, L3 by this combination. And so we can, the conclusion is that we can reformulate the linear gravitational fields in terms of periodic scalar field over the double interval in the X-ray direction. And so now we can go to because we have the equivalence between the polyfields theory in this Casimir box with the periodic field, we can say that the partition function of the polyfields theory is exactly the one is exactly equal to the partition function of phi p, and we can add, as Francesco showed, we can add an additional observable here to make this partition function for phi p. To make it modular covariant, and so it follows that the partition function for the polyfields theory is also modular covariant. Yes, this is what is written here. So it is modular covariant in the parameter tau, as Francesco showed, and in particular for vanishing chemical potential, we recover the inversion symmetry of the Casimir effect. So we have the inversion symmetry of the Casimir effect also in this polyfields theory in the Casimir box. And so now the question is, what is the operator O that we have to add in the partition function to make it modular covariant? And so to find it, we have to translate P3. We have to express it in terms of HMN and PyMN using the map that we developed between the linear gravitational field and the scalar fields. And the expression is a bit complicated. So it is this one, and it involves again power of the Laplacian. And in this gauge, where which is exactly the equivalent of the radiation gauge in electromagnetism, it reduces to this one. To the O has this expression, and so in this case, in this expression, we can see that it is a kind of modified angular momentum, because if we take the Poisson bracket of O and between O and pi, we have up to the power of the Laplacian, we have the expression of an infinitesimal rotation acting on the indices of K. So O has the interpretation up to the power of delta. O has the interpretation of a modified angular momentum. And so now the high and low temperature expansion of the partition function. So they are exactly the same as the one that Francesco showed, because the partition function is exactly the one of periodic scalar field over the double integral. So our high temperature, we have the black body result, which comes from the two polarization of infinite space. So this is the result for if we send the X-ray direction to infinity, and this is the correction, the subleading correction in this limit. And so now the low temperature expansion. There is first the zero temperature Casimir contribution, which is this one, and this contributes to the Casimir force, but it does not contribute to the entropy, because it is linear in the inverse temperature. And next there is the contribution from entry equals 0 gravitons, and this one does not contribute to the Casimir force because it is independent of the the separation between the plates, which is L3, but it contributes to the entropy. So it is this piece is the leading contribution to the entropy at low temperature. And it comes from graviton that have entry equals 0 in the Fourier expansion, and they are subleading terms, of course. And so, if we summarize what we have done, if we choose Casimir-like boundary conditions, we can reformulate the linear gravitational field into two scalar fields, exactly as in infinite space. This allows to compute exactly the partition function of this polyfields theory in the Casimir box, and with modular covariance of the partition function. And exactly as in electromagnetism, the high temperature limit gives the black body result of the two polarization. So in the high temperature limit is exactly the same as the large X3 direction limit, and the subleading correction in the low temperature limit, the subleading correction to the partition function is given by entry equals 0 gravitons, And this contribution is the leading contribution to the entropy. And so some outlooks. One, we have still to fully understand the physical implications of this computation to understand what we can learn from this Casimir computation in the polysphere theory. And also to perform the same analysis in other geometries like the spherical capacitor and in curved backgrounds also. But the problem is that it is really difficult to find a set of orthonormal eigentensor of the Laplacian in other geometries, because in this computation we really use the fact that the Laplacian of a two tensor is the Laplacian of each of its components. And when the metric is not delta ij, this is no longer true. So it is to find a complete set of orthonormal eigentensor is much more difficult. And the possibility is to use instead heat kernel methods to compute the partition functions. And so this will be future directions. And as Francesco said also, I forgot that to generalize the computation to higher spins fields. Thank you for listening. And there was this reference in the talk.
Thank you very much, Martin. Any questions, quick questions? Because you kept time, so we are slowly getting back to schedule. Thanks for that as well. Any questions for Martin on the spin 2 case? If not, then I suggest that you unshare your screen.
How to do that? No. I see. Stop
yeah.
share.
And then we should have, I guess, Andrea trying to share his screen.
Yes, let me try.
Hi, Andrea. Good to see you.
Yeah. Nice to see you. So let's see if it works. So do you see my screen?
It's coming up. Oh, you have a lot of work on your plate. So we see your desktop, but not your presentation. And maybe no, there it is. Yeah.
Okay. Sorry. Okay. So thanks for the opportunity to present this work in this very nice workshop. Now we are the word Eiger spins a few times today. So now let's having a talk just directly dedicated to Eiger spins. And this is based on with some ongoing, with some work with Dario Franch and Carlo Heisenberg, and in particular of the last paper that we published this month. So what's the idea? So the idea is that at the main motivation behind our work is just the infrared triangle that has been proposed by Strominger and then explored with collaborators. And what we would like to discuss is what are the key ingredients behind this infrared triangle, and to what theories is the scheme applicable. And clearly, in this kind of considerations, massless particles must be involved. So one thing that one can do is to play, for instance, with matter couplings and see what happens. So to perform some stress test of the infrared triangles if one changes the details of matter couplings. But even looking only at the universal, or the would-be universal sector of massless particles, the gauge sector, there are still two parameters that we can, with whom we can play with. So one parameter is the dimension of space-time, and the other parameter is the spin of the massless particles in gauges. So in particular, the first infrared triangle has been proposed for 4 space-time dimensions and for gravity, so for S equal to 2 in 2014. And shortly thereafter, there have been generalization of this picture to to low spin fields, so massless fields of spin 0, 1/2, 1, or 3/2. But what about Eiger dimensions and Eiger spins? So can we say something about these two situations, these two setups? So the idea is that there is one edge of the infrared triangle that is particularly suited to begin the investigations in this direction, and it is the relation between asymptotic symmetries and soft theorems. The reason is that Weinberg leading soft factorization theorems apply to any spacetime dimension and even to any value of the spin of a massless particle. So this brings, well, since we know that originally the Weinberg soft factorization theorem in gravity has been related to the word identities of the infinite dimensional asymptotic symmetries of 4D gravity, so to the BMS symmetry, and it has been argued that this relation with the symmetry was really at the pillar of the universality of soft factorization. It is natural to argue, to ask what happens if we change the space-time dimension and the spin, since we remain in a context in which Weinberg's soft factorization theorem applied. But if one tries to do this, there are two problems. So problem number one is that if the dimension of space-time is greater than 4, one can impose boundary conditions that kill supertranslations, essentially, while still allowing for radiation. So the original reasons that brought BMS to introduce supertranslations was the impossibility to recover asymptotically the Poincaré group without killing radiation. In higher dimension, this problem is not there. So apparently there is no need for BMS symmetry if the dimension of spacetime is greater than 4, in the sense that one can set boundary conditions that allow for radiative solutions, but that kill completely supertranslation symmetry. And there is also another problem, and it is the fact that Weinberg theorem is one of the strongest no-go theorems against Eiger-spin interaction, in the sense that if one consider well, the most simplest couplings between matter and Eiger-spins, Weinberg's theorem, factorization theorem, imply the triviality of S matrix for S greater than 2. So I will answer later why I still think interesting to consider values of a spin that are greater than 2. Still, in spite of these problems, there have been some progress in the direction of playing with these two parameters. And first of all, new boundary conditions has been imposed in dimension greater than 4 in gravity and gauge theories, where by gauge theories I mean Young-Mills. And these new boundary conditions allow to recover supertranslations, or they are analog in Young-Mills theory, even in dimension higher than 4. So this infinite dimensional symmetry has been recovered essentially in two ways. So one possibility has been to just impose the same falloff as d equal 4, and this almost trivially led to the presence of infinite dimensional asymptotic symmetries. And interesting enough, even analyzing different asymptotic gauge fixing, it has been possible to recover asymptotic, to relate infinite dimensional symmetries to memory effects in dimension greater than 4. And so this is the second point in my list here. And you will probably see more about the first approach also in Ankit talks tomorrow. Another progress has been the observation that if one considers a generalization of the Bonte gauge to higher value of the spin, one can obtain higher spin supertranslations in d equal 4. By higher spin supertranslation, I just mean asymptotic symmetries that depend on an arbitrary function on the celestial sphere. And moreover, in 2017, within the same work, we also showed that higher spin supertranslations, the word identities related to these symmetries, imply Weinberg's soft factorization theorem. So at least this link has been clarified a few years ago in the case of 4 spacetime dimension. And more recently, we managed to combine the previous two observations to also identify higher spin supertranslation in dimension greater than 4, and to relate them to Weinberg's soft factorization theorems in dimension higher than 4. And as a byproduct of our analysis, we also managed to identify higher spin superrotation, so a larger class of asymptotic symmetries that I'm going to discuss in dimension greater or equal to 4. So in conclusion, what is the picture that is emerging? The picture is the following. It's the fact that there is at least one infrared triangle that essentially only depends on the free theory. So this infrared triangle is relating the asymptotic symmetries of a free gauge theory to leading Weinberg-Soft factorization theorems. And there is also a counterpart, at least for spin equal 1 and spin equal 2, with linear or ordinary memory effects. And this triangle is valid in any D for gravity and Young-Mills, and this link between asymptotic symmetries and soft Weinberg factorization theorems has also been proven to be valid in any D and for any value of the spin. Here I said in any even D because due to some technical complication, our analysis right now, the analysis of this relation only apply to even dimension, although we do identify as infinite dimensional asymptotic symmetries in any space-time dimension. Here I said the free infrared triangle, of course, is not completely true, but it's only, so most of the key universality properties are actually encoded in the kinetic term, or if you wish, in the free theory. On the other hand, you also need some assumptions about matter couplings in order to be able to write factorization theorems. And essentially, in this setup, the assumptions that allowed us to relate asymptotic symmetries yielding soft theorems are quite natural. So essentially, if you consider matter couplings of a form, of the most natural form, as you can see here in, so this kind of, this paragraph is taken from the introduction of Green, Schwartz-Litten books on string theory, where they introduced where we discuss Eiger spin particles present in the string spectrum. They postulate for some arguments in the introduction a coupling of this type, and this is more than enough for what we are gonna do. And but before moving to the details of the symmetries that we identified, let me also come back on the issue: why do we care about arbitrary values of the spin? Well, there are two reasons. So one reason is that you would really like to understand up to which extent the universality of the infrared triangle apply. And most importantly, there is, so string theory has long been considered as being a broken phase zone as an Eiger spin theory, or if you prefer, Eiger spin symmetries are expected to emerge in the high energy limit of string theory. So in this sense, it will be interesting to identify remnants of the symmetries that I'm going to discuss in the following into high energy limit of string scattering. And let me also mention, it has been already mentioned today, that this kind of symmetries that I'm going to describe also appeared in an interesting near horizon analysis by this collaboration, where in a pure spin 2 context, but looking at the possible boundary conditions that one can impose near the horizon, the same type of symmetries emerged. So now let me move to the details of the, a bit more into the details of the analysis that we performed. So what is the setup? I can describe an Eiger spin symmetry just by using this free action, that is the action of Fronsdal. And this action just reduced to the Fierz-Pauli 1 if one imposes S equal to 2. And like Fierz-Pauli action is invariant under linearized diffeomorphism, these symmetries this action display the following gauge symmetry, where parentheses denote the symmetrization of the indices. The only difference is that here I can only allow for traceless parameters. And just not to scare you with the following formula, let me stress that sometimes I will use a shorthand instead of putting a lot of indices with dots. I will just use a collective label to denote a set of symmetrized indices. So this is not particularly important, but just to if you see this kind of symbols in the following formula, this is their meaning. And what completes the setup that we that we used is the fact that we are going to work in retarded Bondi coordinates and study the asymptotic flow-off, the asymptotic behavior of the fields in these coordinates. And another simplifying assumptions that we used, we are going to work in a sort of Bondi-like gauge. This means a generalization of a Bondi gauge for S equal 2. In practice, this means that all radial components of the fields, independently of the spin, will be equal to 0. So for spin 1, this is just the radial gauge fixing. And we will also play with fields that are traceless. And these conditions, you may remark that I'm imposing more conditions than components of the gauge parameter, but this is a sensible on-shell gauge fixing, or you can think at it as a first part of my way of defining the boundary conditions. So this is the first part of my boundary conditions, and now I have to decide what I want to do with the remaining field components that are not necessary to 0 by the Bondi-like gauge. So here there are several options. So in the case of D equal 4, in analogy with gravity, if one has, I lost my mouse. Okay, well, you can look at the first line. So in D equal 4, well, no, it's gone. In D equal 4, one can impose, if one wants to have wave solutions of the field equations, so if one wants to have waves that reaches null infinity for particle of any spin, one can impose the boundary conditions in the first line, where essentially here you have u s minus k says that I taking the components with s minus k u indices and k indices that takes values on the and k angular indices on the celestial sphere. And for a component of this type, I'm imposing the following boundary condition. And the result, as we have proven in 2017, is that by imposing this boundary condition, one can keep infinite dimensional symmetries. So in particular, a generalization of super translations, that means symmetries generated by an arbitrary function of the celestial sphere. On the other hand, if we impose similar conditions in any dimension, so if we just want boundary conditions on the gauge potential that are those typical of radiation, one obtains the boundary conditions that are written in the second row. And for s equal 2, you encounter the problem that I already anticipated. So if I impose this kind of boundary condition, I introduce a dependence on D, and the boundary conditions are such that asymptotic super translations are killed. Or more in general, this kind of boundary conditions are such that only global killing symmetries are kept within my asymptotic symmetries. Or again, once again, the algebra of asymptotic symmetry is finite dimensional. On the other hand, also for arbitrary values of S, we can play a similar trick to the one that has been played for S equal 1 and S equal 2, and keep the same boundary conditions as in 4 dimensions, also in higher D. And this is not a surprise that we will obtain an infinite dimensional symmetry algebra. And in the following, I will focus on this third line of my table. So to begin with, let me look at the boundary conditions that I introduced before, and let me look only at U independent asymptotic symmetries where U is retarded Bondi time. And if I look only at U independent residual symmetries, I obtain residual symmetries that are generated by the following gauge parameters. Okay, my mouse is back. Where here we have a symmetrized K symmetrized gradients acting on T, which is an arbitrary function on the celestial sphere. And in general, this projection is a projection that is contains some terms that are proportional to the metric on the celestial sphere. So if you want to have a more concrete examples, these are the gauge parameters that generates the residual symmetries of a Bondi-like gauge, the U-independent residual symmetries of a Bondi-like gauge for a spin equal to 3. A priori, there are also other components of the gauge parameter, but all the other one can be expressed in terms of the one that I'm writing here. And this kind of asymptotic symmetries is compatible with the boundary conditions or with the fall-off that I recalled in the third line of the previous table, but they are not compatible with the fall-off of radiation. And then, so this explains why there is a differences between these two setups. And now you can say, okay, you got these infinite dimensional symmetries, but what is their meaning? So are they physically acceptable? Because it's not a surprise that you get these symmetries if you keep the same boundary condition d = 4. The problem is that you have to explain me if this boundary condition makes sense or not. And to answer this question, let me share with you two observations. So the first observation is that on shell, all overleading terms must be of pure gauge type. So this means that the term that you see here is a term that is generated by an asymptotic symmetry, and then there is nothing until we reach the order of radiation. So this means that for S = 1, where essentially most of all local observables can be written in terms of the field strength that is gauge invariant on the nose, we have no problems in adding these additional terms. So the idea is that you just modify the gauge potential, but we didn't modify the field strength. And the second observation is that these additional terms do not contribute to surface charges. In which sense? So if I compute surface charges, I find this nasty expression that depends on the on the generator of supertranslation of the arbitrary function of the celestial sphere and on the field components. But actually, if I perform this sum that I have here, because several field components contribute to the surface charge, I find a sum here, a coefficient, an overall coefficient that is actually equal to 0. So the overleading terms do not contribute to the charges, but still I have a term that that is related to the contribution of radiative solutions, essentially inside the charge. So so to summarize, the overleading terms that I introduced in order to have these infinite dimensional symmetries do not contribute to surface charge, but actually a contribution which is divergent, a divergent contribution from radiation is still present. And in spite of this, we proposed a prescription to cure this problem and giving the correct word identities that gives Weinberg's factorization theorem. And the idea is just to assume that before a certain U0, the fields are stationary, then compute the charges on this stationary configuration. And in this case, the charge is manifestly finite, and then define the charge as the evolution under the equations of motion of the result that we get on stationary solutions. If one apply this prescription, one obtains this final result that essentially depends only on the components of the field with only U indices, and correspond where these U0 correspond to the contribution to these components that comes at the Coulomb order. And with this charge, one can take this charge and substitute it and use it to recover Weinberg theorem using the techniques that by now become standard. So the idea, just to sketch the steps, you can see the details in the papers, or we can discuss them later. So the idea is that one first rewrite the charge as an integral over U, and then thanks to the possibility of rewriting the charge as an integral over U, one can use the equations of motion to express this contribution that I recall U was a contribution of the Coulombic order in terms of the value of the fields at the radiation order. So this object is the generalization of a bond in use in the case of Eiger-spin. So all in all, the charge following this procedure is rewritten in terms of radiation data that, for instance, can be expanded into oscillators for the field asymptotically. And putting all this information together, we arrive up to observation number 3, that is that Weinberg's theorem follows by substitution of this charge inside the following word identity. And I record here Avery-Schwab because this is essentially in the paper we followed the approach of Avery-Schwab that has some slightly differences with respect to presentation differences with respect to Strominger way of performing this computation. So in conclusion, we have boundary conditions that allow to define, that allow for infinite dimensional symmetries. We can define charges for these symmetries, and we can use these charges in order to recover Weinberg factorization theorem as a soft, as a word identity. Okay, but now, so that was nice for the case of super translation. But now let me go back to the problem of classifying the residual symmetries of the Bonte-like gauge that I introduced. And for simplicity, let me look at the case of spin 3. Well, actually, if we only classify all residual symmetries of a Bonte-like gauge, the result is the following. So we recover the super translations that we have found before, but we also recover additional symmetries. So super translations are encoded in this function f, and we also have a function v and a function k, and this function can be expressed in terms of tensors, of arbitrary tensors on the celestial sphere of spin 0. So our arbitrary function will generate super translation 1, this function rho, and 2. Rank 2, so this function k. And so these are all the symmetries of my Bonte-like gauge. And now I can see what are the induced variation on the other non-vanishing components of the fields. And this is the result. So look at the order r to the 4, there is a dependence only on k. At the order r to the 3, we have a dependence on rho. And at the order r squared, we have a dependence only on t. And now I have several options at my disposal. So one possibility, I can say that all of them are equal to 0. And this is what I have to do if I want to look for Killing symmetries of my gauge theory, or is what I am forced to do if I impose boundary conditions that in which the gauge potential have a fall-off that is the one typical of radiation, because essentially radiation is subleading if d is greater than 4 with respect to the orders that you have in this expression. So if we impose all this term is equal to 0, only global Killing symmetries are kept. But I can do what I have done before. So I can just decide that to impose boundary conditions such that the latter equation does not have to be imposed, and then I don't have any additional condition on t. So this means in particular that I have t is a free function, and this gives the super translation that we have discussed before. Still, with this boundary condition, I keep these two terms equal to 0. And these two equations actually have a different behavior if d is equal to 4 or d is greater than 4. Because if I only look at the global symmetries, actually there is no difference. So if I look only at the globally well-defined solutions of these two equations, so this term is equal to 0 and this is equal to 0, I only found the generators of the generalization of Lorentz symmetry. So I only find a finite number of asymptotic symmetries. On the other hand, you can realize that in the first line, there is the generalization of the Killing vector equation, that is the conformal or the conformal Killing vector equation that applies to tensors of rank 2. And similarly to the conformal Killing vector equation that is probably familiar to all people in the audience, this equation admits infinitely many solutions locally in D equal 4. So in D equal 4, I can recover super rotations even by imposing Eigerspin super rotations, even by imposing that these two terms are equal to 0. On the other hand, I can even do more. I can simply decide that my boundary conditions are such that no constraint is imposed on these conditions. And in this case, one recovers super translation and super rotations in any space-time dimension, actually. But okay, so again, this looks like a triviality, but does this make sense? So the idea is that if one imposes even weaker boundary conditions of this form, Eigerspin super rotations can be recovered in any space-time dimension. So what is the interpretation of this result? Well, let's look for S equal 2. If we look at S equal 2, in this case, the variation that we are allowing takes the following form. And you see that we are allowing symmetries that are generated by an arbitrary vector on the celestial sphere. So this means that we are just generalizing to any dimension the super rotations of Campoleoni that has been proposed by Campoleoni in 2014, as that have been recalled also in previous talks. From the higher spin viewpoint, the fact of having these infinite dimensional symmetries just means that if I look at the global higher spin symmetries, they are in one-to-one correspondence with this Young tableau. So if you look at the case of spin 2, you will have translations that are just a one-box Young tableau and rotations that are just an antisymmetric Young tableau. While in the case of higher spin, the global symmetries are enlarged and are in one-to-one correspondence with these Young symmetries. And what I'm saying is simply that with these weak boundary conditions, each set of these symmetries gets an infinite dimensional announcement. This infinite dimensional announced. So do these symmetries make sense? Well, one thing that we can already say is that overleading terms are still pure gauge, even for super rotation. So in this sense, the situation is as good as for the case of super translations. And as I will flash in the following slides, this analysis brings an extra bonus. So this means that brings another interpretation of these symmetries in the sense that allow to see that these symmetries are in one-to-one correspondence with partially massless representation on the celestial sphere of a conformal group in d-2 dimensions. Then. On the other hand, the analysis of charges is likely, more complicated but also this is not a surprise in the sense that the same is true also for S equal 2. And in spite of these, there are some good indications. So for instance, as we have seen in Adrien's talk, it is possible actually to renormalize the charges that are associated to Campoleoni super rotations. And similar charges has been used by Colferai and Dionetti to derive the sublinium soft theorems in any even space-time dimension. So there are some good indications that these things may make sense also in higher dimensions, but the analysis is less complete with respect to the one that we have been able to perform for super translations. And before concluding, I would like to just briefly mention this relation between super rotations and partially masslessness. And this is related just to the proof that the overleading terms are actually pure gauge on shell. And what's the idea? So the idea is that you just take a radial expansion of the fields in Bondi coordinates. And above radiation, essentially all components in this radial expansion are proportional to the components in the expansion of the field component without any U index, that I will call them C. And the equations of motion impose the following equations. And if you look at this term and at the value of n that correspond to the contribution of radiation, the prefactor here just goes to 0. And then we have an equation for the components that stay just above radiation. And the point is that the differential operator that you find here is invertible. Here you have 0 on the left-hand side. And so we can use this equation to set to 0 C. This kind of procedure continues iteratively until we hit a place where this cannot continue because it is the order at which these asymptotic symmetries are present. And this can be understood from the point of view of the equations of motion, also considering this small shift, but allow to rewrite this operator on the right-hand side of this equation in the following form. Sorry. And these operator just admit a gauge symmetry. And this is the reason why it's not invertible anymore, because this gauge symmetry is there, and this gauge symmetry is related to the presence of asymptotic symmetries. And the relation with partially massless field is just due to the fact that if you look at the form of this operator that we have here, you realize that the components 1 minus s minus t just satisfy as here, an operator of the form box plus minus m square, when m square is really the mass value of a partially massless field of spin s and depth t. And there are s minus 1 of them, and this is related to the fact that we have s minus 1 classes of asymptotic symmetries. And so that was the conclusion of my talk. So just to a small summary is the fact that you can extend the infrared triangle to any S and any D, or at least the link between asymptotic symmetries and soft theorems. And you can also impose weaker fall-off conditions that brings to any S superrotations. Of course, what's next? It would be to try to better understand the renormalization that is needed to define well-defined to define finite superrotation charges. And of course, up to now, the analysis has been related to free theory. But if one really wants to understand remnants of these symmetries in string scattering, it will be important to have some non-abelian Eiger-spin algebras that fits inside this, this framework. So thanks.
Thank you very much, Andrea. Any very quick questions? I think we get a bit of non-abelian stuff in the next talk, hopefully. So, we'll see about it.
Here is a very light question to ask you. So with this kind of new boundary condition, is there any kind of calculation for memory effect?
Well, what do you mean for gravity or for higher spin?
For high spin.
Well, for higher spin, the problem is that you have to tell me what a memory effect is for higher spin. So you have to specify the coupling of test particles to higher spin gauge fields. So we are there are some formal counterparts of memory effects on which we are working on. But if you really want to tell me what a memory effect is, first you have to tell me how the source, how the test particles couples to higher spin. So it's a kind of subtle question. It's much more direct to understand the relation with Weinberg's soft theorems. But in the case of gravity, yes, there is a relation to memory effects also in higher dimensions, although it's even a bit more complicated because the asymptotic symmetries that are linked to memory effects are not exactly the same that are linked to Weinberg soft theorems. So there are somehow two branches of super translations that are needed in higher dimension.
Okay, got it.
Okay. There's a question by Marc and then by Luca. So Marc, please.
Okay, yes, I have a question about matching conditions. Did you work out the matching conditions for higher spins? I mean, the so-called matching conditions as Strominger wrote them.
Yes, well, we just generalized trivially the matching conditions that are in Strominger. Yes, so this is an ingredient that I haven't stressed in the presentation, but matching conditions are necessary in order to recover Weinberg soft theorems.
Okay,
yes.
Thank you.
Okay, Luca.
Hi, Andrea. Simple question, hopefully. I've been pondering recently about large D gravity. Do you have any comment since you're working in possible any D? What about specifically very large D? Recently, you know, Roberto and Paran has been working on this. There was a review. Do you have just any idea of what is going on here? I guess the radiation become extremely subleading in the bulk.
Exactly, this is correct. So you see it, well, now I don't know if I will manage to go back. So essentially, yeah, you can see it in this table. So essentially the boundary conditions that you need in order to keep these asymptotic symmetries are D independent. While the contribution of radiation goes like r to the minus d divided by 2. So if d becomes very large, radiation becomes very subleading, but this doesn't change anything. So, I mean, somehow here, the setup that you have in any D is close to what you have in, so you can think at very large D as something similar to what you have in D equal 3. In D equal 3, you don't have any local degrees of freedom, but still you have an interesting asymptotics and an interesting boundary structure. So this is exactly the same. So in D equal 4, just by chance, the interesting asymptotics and the radiations and the physical degrees of freedom are in the same order. But this is just a sort of a peculiarity of D equal 4. If you increase the space-time dimension, simply the boundary degrees of freedom remain at the same order, and radiation starts to go down in order and become less and less important. So greater is the dimension, closer you are to 3D in a sense. Of course, degrees of freedom are still there, but they are less and more subleading.
But the bulk dynamics is changing, right? There are this discussion about Gregory-Laflamme instabilities and things like that. So maybe, you know, you may see something from your asymptotic perspective on that. It's
yes.
very different than d=3, the bulk itself.
No,
right?
no, that's true. So I was just saying that there is this decoupling between degrees of freedom and between boundary degrees of freedom and really physically propagating degrees of freedom. For the rest, as far as this analysis is concerned, well, the fact that the dynamics is different, well, somehow is not so crucial because I'm just looking at the free theory right now. And also most of the analyses that have been performed, also the original one in S=2, actually mainly dealt with the free theory because they were looking at an asymptotic expansion. And of course, it will be interesting to see what happens if you start including interactions, for instance, in gravity, like nonlinear effects, nonlinear memory effects, and subleading soft theorems, essentially.
Excellent. Thanks a lot. Thank you.
You're welcome.
Okay, so I think we should move to the next speaker. Can you unshare your screen? Andrea, thanks very much for the presentation. Hello, Roberto.
Hello. Can you see my presentation?
Good, very nice.
Okay.
So just
So let's
take it away, and you have till 6:15 past 6.
Okay, yeah, I will try to keep track of the time. Okay, so to begin with, I would like to thank very much the organizer for the invitation and for having organized this very nice workshop in this very difficult situation. And my talk is going to be based on the results contained in a paper which I recently published together with my supervisor, Domenico Giulini. And it's about the asymptotic symmetries of Young-Mills at spatial infinity. So just as a motivation, we have seen very many talks already about some of similar topics. And previous study covers many studies at null infinity, and in particular for gravity, electrodynamics, and Young-Mills. And there has been some very nice studies by Henry and Troessaert at spatial infinity, covering, among others, gravity and electrodynamics. And so Young-Mills is in some sense missing from this picture. And so my study comes exactly in order to complement this lack. And the goal is to find a well-defined Hamiltonian formulation of Young-Mills. And after we've done that, to study what asymptotic symmetries we have. And the motivation for going to the Hamiltonian formulation where they have been already mentioned. And just for a quick review. So mainly, well, the two approaches at null and spatial infinity should be equivalent. But despite that, they could highlight different aspects of the theory. Second, because the Hamiltonian formulation is very good to study the symmetries of the theory. And the third is because it's the base of the canonical quantization of the theory. And so I would like to give a very small introduction of what is Young-Mills and what I mean by well-defined Hamiltonian formulation, although many speakers have already given this bit, but I will give a very small review. So yeah, after we talk about what is Young-Mills and the Hamiltonian formulation, I will give you the condition that one needs to impose in order to have a well-defined Hamiltonian formulation. And after we did that, we were going to discuss a bit what are the asymptotic symmetries. And finally, we go to the conclusions. So in 2 slides, what is Young-Mills and what is well-defined Hamiltonian formulation? To begin with, we need a phase space. That's the most important object. So you can see it as the set for allowed field configurations. So I'm going to denote it by P and Q just very generically. And we need to say how big this set is. So we have to impose condition on P and Q so that the rest of the theory works. And we give the phase space structure of a manifold so that we can do some operations. So in particular, we can take the exterior derivative, which is in some sort in some sense related to a variation, and we can consider vector fields that are somewhat related to infinitesimal transformations. And so I'm going to denote vector fields with a capital X and with a subscript denoting which vector field is. And their components are going to be denoted mostly with a delta, and then use this transformation. And then we need to have two very important objects. So the symplectic form, which is a closed form on the phase space, and it needs to be and it needs to be finite. So it's going to be given as an integral, yeah. And we need to make sure that this integral is finite, otherwise we don't have the Poisson bracket. And finally, we need to have a Hamiltonian, and the Hamiltonian needs to be differentiable. So it's been already covered in many talks. This is one of the most important equations. And to finish it, this will be fine for every theory, but since we are dealing with Poincare invariant theory, we also want the Poincare group to act in a canonical way, so to satisfy the same equation for a different vector field. So just very quickly, what is Young-Mills? This is the action of Young-Mills. I wrote it in a way that it resembles pretty much the action of electrodynamics. So it has several ingredients. So to begin with, we have A, it's a one form, but instead of being made of real number, it's made of matrices, so they do not commute, and that's where the non-abelian part of the theory comes. And so they need to be anti-emission matrices and traceless. And if we want to find SUN, starting from the Lie algebra SUN, you need to take the exponential. Then you have the field strength, which appears in the action twice. And it's very similar to the one of electrodynamics. And it only contains a new piece, which is a commutator. So that's precisely the term that differs from electrodynamics, and that's going to play a big role in the following discussion. So basically we have a commutator here, and we also have a killing in a product, which is positive definite in my convention, and it's given by the trace of these matrices. And if you want to recover electrodynamics, you just need to make this trace to be just the product among real number, and this cross to be 0. And very importantly, there's need to be a boundary term in the action, otherwise its variation is not well defined. So the Hamiltonian of free Young-Mills is given in the following. So we have two canonical fields. So this would be the Q and this would be the P, and they are the spatial part of the one form we had. And then there are this pi A, if you look at it in electrodynamics, is somewhat related to the electric field. And so you can see it as a generalization of the electric field for the non-abelian case. And then the symplectic form is just a standard d pi wedge dA, but it could contain a boundary term because the action could contain a boundary term. And the Hamiltonian is written in my notation. It's just the same. It looks just the same as the one of electrodynamics. And also in this case, one needs to include a constraint into the Hamiltonian with a generic Lagrange multiplier epsilon. And the constraint is again very similar to the Gauss constraints, but now contains also a commutator of A and pi. And if we take the equations of motion, so if we take the H and we look what's the result, we are going to get the following expressions. So as you can see, this first part of the Hamiltonian gives rise to the usual equations of motions. And when we vary the constraint, we get these arbitrary gauge transformations in the equations of motion. So I want to give a very very quick example of what it means to do this D, although it's been already shown by some of the previous speaker. And this also allows me to introduce what is gauge transformation. So gauge transformation are basically those transformations that are generated by the constraint. So it's precisely those transformations generated by this guy here. So we just take the constraint, we just take its D, so its variation. And if we do so, and you rewrite the terms, you're going to end up with an expression that depends on the variation of pi, the variation of A, and it contains also boundary term. And now if you compare to minus Ix omega, you have an expression which depends on dpi, it depends on dpa, but does not have a boundary term. So from this expression here, you see that the transformation of A under a gauge transformation is minus dA epsilon, and the transformation of pi A under a gauge transformation is epsilon cross pi A. But you need to make sure that this boundary term vanishes. And when this happens, then you can also compute the algebra. You can take the Poisson brackets of two gauge transformation, epsilon 1 and epsilon 2. You get again a gauge transformation, which is given by the commutator of epsilon 1 and epsilon 2. And this relation is telling us that we have, so G gives us a posterior representation of the algebra of SUN. As we've seen in many other examples before, we can redefine these generators G by adding to it a boundary term, which we call Q, so that it's always differentiable. So when you take the variation of this new guy, this extended G, you do not have any boundary term. Now, this is generating a transformation, but this transformation is not a proper gauge transformation because it's not only generated by the constraint, but also by a surface term. And one also note that it would be a symmetry in the sense that it commutes with the Hamiltonian. But before one does make this statement, it's better, one needs to be sure that this transformation is compatible with the condition what gives on the phase space function. So in a sense that this is a well-defined vector field on phase space. So let's see what could, how to give a well-defined Hamiltonian formulation of Young Mills, and I will come back to that point later. Okay. Giving a well-defined formulation of Young Mills means the most important part would be to decide how big the phase space is. And we have to decide how big the phase space is in order to make the symplectic form finite, to make H and so the Hamiltonian and the generator of Poincare transformation to be finite and well-defined differentiable. So we begin with writing the Poincare transformations. These are the following transformation. They can be derived in several ways. I'm not going through the derivation. We are just going to take them for granted. And they can be decomposed in three parts. So there's one orthogonal part, which is here and here, and it couples the field with its momentum and the momentum with the field. And then there's a tangential part here and here that acts through the Lie derivative of A and the Lie derivative of pi. And finally, one needs to complement the Poincare transformation in general with a gauge transformation. And if you look how they decompose this tangential and perpendicular part, well, they contain the boost, they contain the space translation, and they contains the translation in is it time translation, space translation, and finally they contain the rotation. Okay, the observation is that we can derive Farloff conditions for the fields using the following three assumptions and nothing more. So the first assumption is that we take the fields to be power-like. For instance, for AR, we would impose that AR goes as 1 over R to some power, say alpha, times a function that depends on the position, plus some sub-leading order. And we do the same for all the other fields and momentum. And the second condition is that we impose these Farloff conditions to be preserved by the Poincare transformation. And finally, if we have more than one solution, we take the more general one. Under this assumption, one can determine uniquely the Farloff conditions for Young mills, and they are the same as they are in electrodynamics. So let's see, AR goes as 1 over R, pi R goes as 1. And this means if you convert it into the electric field of electrodynamics, this means that the electric field, the radial component goes as 1 over R squared. So this is the well-known equation. And okay, if you look at these conditions, you need to know that if you take the field and you take its momentum and you take the product, they always go as 1 over R. So 1 over R times 1 and 1 times 1 over R. And we also have some condition on the gauge parameter. So the fact that when we take the product, we get a function of 1 over R, which means that we have a problem, and namely that the symplectic form is logarithmically divergent. So in particular, it contains the following logarithmically divergent contribution, which can be written as d pi r dAr plus d pi a bar dA bar. And we already know what's the solution to this problem. So we basically ask this field to have one parity under the antipodal map, and we ask the momentum to have the opposite parity. And we do the same for this field. So we ask it to have some definite parity and its momentum to have the opposite parity, so that in total here, we get an odd function of the sphere. And so this integral becomes 0, and the potentially logarithmically divergent contribution is in fact 0. And another observation is that this parity condition can be determined with two requirements. So the first requirement is that they need to be preserved by the Poincare transformation. And the second requirement is that the Poincare transformation needs to be canonical. Okay, so let's see the first one. Yeah, so the first one is the Poincare transformation preserve parity if and only if sigma, so the parity of this guy, of the angular part, is 1. So if this guy is an odd function, let's see how I can see this. So we just take the Poincare transformation we had before, and we expand it in power of 4, and we make a comparison of the leading orders. So what we get is this very big expression. We don't need to look at the details. The most important part is that they depend on the boost, the red part. Then it depends on the rotation, the blue part, and the dependence of the rotation is always given by the Lie derivatives as vector fields on the two sphere, and then it depends by the gauge parameter. Okay, and then you also need to note that you have here some operator which is given in terms of a derivative plus a commutator. And now if you take the derivative of a function of definite parity, you get a function with the opposite parity. So in a sense, the derivative acts as a node operator. And if you want this gauge covariant derivative to be of well-defined parity, you need to ask that AM is of odd parity, which is exactly the condition I've given. So the only thing you need to remember from the asymptotic Poincare transformation is that if you take this guy to be of odd parity, everything is consistent. And now in order to determine what is the specific parity condition for the radial component, we just look at the Poincare transformation. Okay, requiring that they are canonical means to say that they satisfy this equation, which means that this one form here needs to be exact. And for the Poincare group, this condition is equivalent of requiring that this one form here is closed. And if we do the computation of this guy here, we will get a boundary term. So the two things to note is that after all the fall-off conditions have been imposed, the contribution for which the Poincare group fails to be canonical is at most a boundary term, and that this boundary term depends solely on the boost. And now if we take the right parity for AR, we can make this solve function to be an odd function so that its integral is 0. And in particular, you need to take AR to be even, then the momentum needs to be odd. We already said that A bar needs to be odd, and the momentum needs to be even. And if you compare the situation with electrodynamics, in electrodynamics, you would have the same choice. And in addition to that, you would have exactly the opposite parity choice. And the one you actually take for the electrodynamics is the second one. So the one you don't have for Young-Mills. And you do that because it contains the Coulomb solution. So that's the first difference between Young-Mills and electrodynamics. So the equation looks very similar in many aspects, but then it contains these new terms that impose some stronger constraints on the condition we can impose. And so to summarize what we've done so far, we have derived the fall-off and parity conditions so that we have a well-defined Hamiltonian formulation. And namely, we have a finite symplectic form. We have a Hamiltonian which is differentiable. And we have an action of the Poincare group, which preserves, on the one hand, the fall-off and parity condition, and on the other hand, is a canonical action. And the two issues that one could find so far is that imposing this fall-off and parity condition does exclude from the theory improper gauge transformations. And basically because the improper gauge transformations would change the parity of the leading term of the asymptotic fields. So improper gauge transformations so far are not included. And the second thing is that if you took the total color charge evaluated at infinity, then that's 0. So this would be this integral here. So it's when epsilon 0 is a constant, doesn't depend on the angles. And since this function here needs to be odd, when you do this integral is 0. Now, so what are the asymptotic symmetries? If we want to include again the improper gauge transformations, we need to try to relax a bit the parity conditions. And it's been already shown how it works with electrodynamics. So you basically introduce them back by force. So you take the fields to be of a definite parity up to an improper gauge transformation. And you do the same thing for Young-Mills. So you try the same, to play the same game. So you take the fields to be of definite parity up to an improper gauge transformation, which I denote by U bar. As a consequence, so you're losing two of the very nice properties you had before, and namely the first one, you're going to make the symplectic form to be not finite anymore, and you're going to make the Poincare group to be non-canonical anymore. So let's look at the symplectic form. If you compute now what's the logarithmically divergent contribution you have there, and if you do some algebra, you will find out that it can be written as a sum of two terms, and each one of the two terms contains the Gauss constraints evaluated at infinity, so that we can make the symplectic form to be 0 simply by imposing that the Gauss constraint evaluated at infinity, the asymptotic part of the Gauss constraint is 0. So in other words, we had we had Farloff condition and parity condition to define our phase space. We relax the parity condition so that the phase space becomes a bit bigger, and then we impose an extra condition that makes it a bit smaller, but still larger than what we had with simple Farloff and strict parity conditions. So this solves the part for the symplectic form. And now very quickly, let's see what happens to the Poincare transformations. So the Poincare transformations are not canonical because this term is not anymore 0. So for electrodynamics, it's been already shown to us that you can introduce new fields of phi and pi. You make them trivial in the bulk, and you add a surface term in order to compensate for this contribution. And you also need to extend the Poincare transformation. So in particular, these new fields that you introduce psi needs to transform in the following way. Now the problem is that if you try to do the same trick now with this solution phi and psi, psi and pi psi, it does not work because you cannot get rid of this term here, which is a term containing solely the A without any derivatives. And if you try, so what we did in the paper is we tried to introduce other fields, so we call them phi, that transform directly as A in order to compensate for this term. We made them trivial in the bulk by imposing this constraint, and then we tried to make a very general ansatz for the Poincare transformation, the extended Poincare transformation, and for the symplectic form at infinity. And we tried to check if for some parameters, for some value of the parameters contained in this ansatz, we had this equation to be 0, and the answer is not. And we also noted that further extensions are likely to come from an action principle. So in conclusion, very quickly, we found a well-defined Hamiltonian formulation of Yang-Mills, imposing Farloff condition and strict parity condition. So the two things, so the thing that we noted is that we cannot relax these parity conditions so that the color charge is always 0, and the asymptotic symmetries is trivial. So in the sense that it's the Poincare. And finally, if you try to relax a bit this condition in order to include non-zero color charge or non-trivial symmetry, you either end up with a non-finite symplectic form or with a non-canonical realization of the Poincare group. And so the two questions I have is, well, is how do you compare with the situation at null infinity? Is for some reason maybe the symmetry at scribe plus minus non-canonical, and the second thing is this fact that the color chart needs to be 0 in our formulation, a hint towards a classical manifestation of confinement. Now I think I've exceeded a bit my time, so I'm going to leave
No, not at all. You have been perfect in keeping your time. Thanks very much. Thank you for a nice talk.
So I will leave, yes, the time for the questions and the discussion. And if you want to have more details, you can read the paper, and it also contains all the references I've given in the talk. And I thank you very much for your attention.
Thank you. So any quick questions before we all fall exhausted to the floor, or almost? Marc has a question, so let us have him. Please, Marc.
So a quick question. So you have zero charge because pi r, you said, is odd.
Yes, exactly.
Could you explore alternative conditions where it would be even, or I mean, I didn't.
Yeah. That's the problem. The thing was, it was here. If you try to impose strict parity conditions, so before you try to do any extension, you cannot have it to be even. So otherwise, the Poincare transformation are not canonical. So in order to impose this guy here, so if you want this guy to be even, this guy needs to be odd. And in order to make this whole expression 0, I think you need this guy to be even, and you have still problems with the covariant derivative.
But so this is, okay, that's nonlinear, I mean, typical Yang-Mills effect. Okay.
Yeah.
Okay.
So if you look just a strict parity condition, you cannot. Maybe you could if you do the extensions in some way. So if you relax the parity conditions, then you get a non-trivial term and the symplectic form, and this term can be made to 0 independently of this parity condition. So you could in principle take the opposite parity for the radial components and still make the symplectic form finite.
Okay.
I think. But you do fail to have a canonical Poincare transformation. So unless you manage to solve the issue of cancelling these terms at infinity for the Poincare transformation, you cannot flip the parity of pi.
Okay, thank you.
Any other questions for Roberto? I am not seeing any. Okay, thanks very much for the interesting talk. I will look at the Christodoulou Morchada reference. I never saw that one, so I'm looking forward to reading that one. The reference is in your paper, right?
Yeah. And also the discussion, so there are many more details.
Very good.
Yeah.
Thanks very much. So thanks everybody for attending and sticking around. So it has been a long day, so I will not keep you much further. Tomorrow, I think we reconvene at 9:15, is that correct?
Yeah, 9:15.
9:15. Okay, thanks a lot, everybody. See you soon.
Thank you. Bye-bye.
Bye-bye.
Bye.
Ça va, Stéphane? Tu vis encore?